teachers try to get here about a half hour early. And so if there's things that aren't clear in the reading or aren't clear in what you were covered, that half hour sort of pre-lecture is meant to just sort of get the groundwork laid, some of the subjects. And so I apologize if you're stepping in right now. This is still part of that learning curve of how things are done. And you're gonna hear this apology probably 2, 3, 4 different times, but for some of you it'll be time number 2. But I apologize because amino acids should never, ever, ever have been the very first lecture because there's way too much stuff to cover. Oh, you're welcome. Hopefully it helps. It lays the groundwork a little bit. And again, this is stuff. PK is something covered in the acid-base section. Amino acid lecture always comes after the acid-base lecture, always comes after the carbonyl lecture, just sequentially. Josh decided to let Josh be 100% in charge of who's teaching, what the schedule is this time, let him spread his wings and figure out how to do it. And I mean, it's something you learn over time doing this, that you don't put the really tough lectures right out of the gate. You let the foundation one. So part of the reason it's going to be a long lecture today is a lot of the foundation stuff has to just be, I mean, if you have questions, really fundamental stuff that's just like slipped away because it's been a few years, please ask. Because if you don't know what PK or pH have to do anything with, it's really hard to go on to isoelectric point, for instance. So anyway, so yeah, if you're just arriving, that was just a quick little rundown on why, I mean, the 3 questions I proposed just based on typically what people ask. That's just got as far as that PK one. So I'm going to go ahead and switch over. So if you're going to screenshot it, 3, 2, 1, and go on to this. Hey, good morning, Heaven. How are you?
Hi.
So this is hopefully going to be just the rhythm you get used to. If you get here a little bit early, teachers are, I mean, I hope they all do it. I mean, I know last time, like Rachel was good about it, to see a lot of the teachers. So if people got here early, I'm hopeful that can take advantage of that time. So if there's something from the reading that isn't clear, good idea to get it cleared up before lecture starts, like right before lecture starts, even if it's just one silly little definition. So this means it seemed really, really weird that this was such a mind-blowing thing for me. But I remember midway through sophomore year, I finally realized that hydrogen has a proton and an electron orbiting around. If you take away the electron, it's just a proton. So the term protonated came from proton, the H without the electron. And I don't know why that, like when I suddenly realized that's why they say protonated, it's like, whoa, this light went on and suddenly everything became clear. It never dawned on me that why they called it that. And how many have had those little revelations, that small little moment of insight? It's like, holy crud, that it makes all this sense now. So, yeah, and it's weird. It does change everything, and you have those. It's like, oh my gosh, it's always coupled with the why didn't I realize that before? But oh well, I trying to give myself a pass on that sort of thing. Okay, so I think we're getting close to time. Again, I'm looking at the number of people here. So I did this lecture early, so I don't know if we won't have a full house either. Oh, it's time. I'll go ahead and get started because this, again, is going to be a pretty impacted lecture, just a lot of information on this one. And so amino acids, going to do isoelectric points, and real minimally going to touch into protein structure. But I want to start with the concept of amino acid. And am I safe in assuming everybody has taken enough bio to know that amino acids are the building blocks to proteins? Put a whole bunch of amino acids together and you have this chain. So So if you want to build a chain, how many sides do you have to have that can connect to other things? At least two. Perfect. So hence the term amino acid. So if I consider the compound, I'm going to just look at it from an OChem standpoint at first, but an amine is typically a nucleophile. This is a leading group. I put a question mark because how good a leading group is OH? Great leading group, average leading group, terrible leading group. So it is a leading group, but it's not a very good leading group. So if I want to build a protein, do you agree? Number one, this has to stay nucleophilic, meaning it has to keep a lone pair to attack, and I need to do something. So protein synthesis always involves turning the OH into something like a bulky leaving group. Amine tax kicks it out. Amine tax kicks it out, and you start building it. But to build a chain, like a protein, you need two reactive ends. And nucleophile reacts with leaving group, nucleophile reacts with leaving group. And would you agree this is too close? If this was going to come in and attack here, it'd be a three-membered ring, too strained to do it with itself. So you want them two reactive sites close enough together that it can't form a ring. Okay, so feel pretty good about this. So I want to ask you, how would I ever get this form? This looks kind of strange. Would it ever come like that? So why am I doing pH 7.4? Like just kind of a random thing. Nervous habit, but I've seen other teachers do that number. So what do you mean by physiological pH? It's an interesting concept because, for instance, isn't the stomach? I think isn't the stomach like 2-ish, like 1.5 to 2.5 or so, depending on whether you're digesting. pH of blood, I like that sort of, but isn't arterial blood different than venous blood? And I'm trying to be devil's advocate, be difficult here, but it's an interesting term we toss out there, physiological pH. Want to make sure we don't mistake physiological pH for biological pH or anatomical pH. Physiological pH is the pH at which the majority of our enzymes are active. So it's intracellular pH where most of our enzyme activity, what's happening in the majority of our organelles. Blood pH, just to bring it up, how many learned 7.4 is arterial blood, oxygenated blood? But once it gets to the tissue and gases are exchanged, then it becomes rich in, it becomes rich in CO2. And what happens to the pH? Lowers, exactly. Okay, so that's just one of those things. Just want you to hang on to as just one of those key thoughts. But pH then 7.4. I'm going to say that's where most enzyme activity and that's where most of the proteins are going to find themselves. That said, if I told you, for instance, pepsin was optimal at 7.4, would you believe me? Okay, then let me rephrase my question. I believe pepsin is active as an anion. Do you believe me? Oh, the ASH study is happening. How many are saying yes because somebody else said yes? Like, I won't know if you're answering yes to that or not, but so is it the same question? So when I said, first off, pepsin is optimal at 7.4, why did you say no? What do you know as your memorization? So where is pepsin active? Digestive enzyme, active in the stomach. What's a pH in the stomach? Gastric fluids. Oh, perfect. 2-ish, exactly. 1.5 to 2, somewhere in that range, perfect. So if the pH is really low, if we put a lot of acid around, does that have a tendency to protonate or deprotonate the compound? A lot of acid? You sure? If you jumped into a pool with a really low pH, Low pH is rich in acid. Acid will protonate it. When it protonates it, it's going to turn it into a cation. So the key thing here is, yeah, we're going to protonate it and make it a massive cation. So pepsin is probably going to be active in its cation form, its fully protonated form. So does that seem okay then, that the pH is going to impact the nature of the compound? Make it really low, make the compound positive. Make the pH really high, make it negative. So random question, for those of you who've done electrophoresis, do you usually load it on the side with a really high pH or really low pH? If you can recall, for anybody who remembers electrophoresis, and again, I'm getting way ahead of myself, but I'm fishing for maybe the 5 to 10% who actually know it. Okay, you load it usually on the side with like, oh, the question is, when we do electrophoresis on proteins, DNA, whatever we're dealing with, but usually proteins in this case. So if I load it, one end, usually it's a buffer gradient, high pH and low pH. Do I load it at the high pH or low pH end, typically? And as always, I want you to think as simply as possible. Okay, so high pH end, how many get that from memorization? How many just memorize we load at the high pH end? It's what you do. Professor says to do it, lab boss says to do it, you just do it. It does matter actually, and I want to explain why. So technically, yeah, if you're doing isoelectric focusing, it shouldn't matter. But here's why it does matter. Do DNA and RNA carry a negative, positive, or neutral charge naturally? Negative. Okay. If I want my labs to always be consistent, then proteins you read can be positive or negative because they have different side chains. So if I wanted to have consistency, so somebody doesn't screw up and accidentally load a protein the wrong way, I want to make it just like DNA and RNA. So I typically want to load a protein negative protein structure. Or number two, you load the native pH, the native protein at a really high pH. At a high pH, it's going to be negative or positive. Negative. We do this, we make the protein negative just so that now it becomes a little more consistent. I'm doing the same thing. I'm loading RNA, DNA, and proteins in the exact same wells, which means the gels can be consistent for whatever I'm doing. If you could load on either side, you'd have to have wells on either side. So just for simplicity, for equipment's sake, we typically load everything negative because DNA has to be negative, RNA has to be negative because of the phosphate backbone. So we do things to make proteins negative so we can load them in the same spot and have the same consistency from one experiment to another. So there's no magical thing. So Nay, you're actually right that we could do it either spot. We could do it in the middle, could do it left, could do it right. It shouldn't matter. But to stay consistent with all sorts of blotting, we load it at the negative end. And then just one thing I want you to just hang on to this thought. Anions go to the anode, cations go to the cat home. So if I load an anion, it's going to migrate across the gel to the anode plate. It's just hang on to that thought. That'll save you a lot of stress. Don't ever try to worry about the charge of the plates. Instead, just know anions go to the anode, cations go to the cathode. Okay. Whole point of doing this is to emphasize I need to know something about charge of proteins in order to figure out how they're going to behave, how they're going to fold, how they're going to behave in lab experiments like electrophoresis or ion exchange columns. So this charge concept becomes big. So why is this site positive? Why is this site negative? You started to tell me and I went off on this tangent. So let's get back to this. So why is this positive and this negative? pK is perfect. When pH is less than pK and pH is more than pK, it dictates what's going to happen. So 7.4 is less. Less will be protonated. And 7.4 is more. Higher pH, basic feeling, it'll deprotonate. So what do they call this? It's an ion, but it's not charged, is it? It's like a neutral ion. So is that a word, neutral ion? Do you say it really fast together, or do you get fancy and make it some German word? Zwischenreihen. Perfect. Not sure why they stuck with this, but here's my Zwischenreihen. So is a Zwischenreihen the natural way something exists, i.e. a protein or amino acid, in aqueous conditions? Is this the expected state if we have it in a water environment, inside the cell, for instance? Sure. How could I ever get this structure then? In a physiological system, can I ever get an amino acid to look like that? Ah, perfect, Mo. So all of us think in terms of pH because that's how we're programmed. If I lower the pH, I protonate here, but that stays protonated. Raise pH, I deprotonate here, but that stays deprotonated. So you can't do it with pH. You do it with lipid environment. One of those meaning of life sorts of questions. Do different amino acids seek different environments then based on their R group? So naturally occurring aspartic acid, aspartate, is probably going to be found in water more often because it has a charged side chain. So it's going to try to get an aqueous environment. Some like alanine might have a tendency to try to find lipid environments to make that happy. And in doing so, make those neutral. Okay, sounds reasonable. It leads to the first of like the bio applications. So in your travels through bio, did you learn about protein channels? Proteins that embed into the cell membrane and create a pathway for things to get through, whatever things may get through. Okay, so teach me a few things about this. Number one, is a protein going to have various R groups? 1, 2, 3, 4, 5. I think I've listed 11, 12, 13. I've numbered them, haven't specified what they are, but tell me what you think is going to be true about R1, R2, R12, and R14, the even number ones. Hydrophilic or hydrophobic? Even hydrophobic because they're existing in the lipid backbone. Perfect. What about the odd numbered ones? 1, 3, 5, 15, and 13, 11? Hydrophilic. Why? They are not in the lipid. They're trying to get away from the lipid, so they form here. And somebody mentioned, is this going to be water filled in? Is this a water-friendly environment? Can water migrate through? Sure, bridging waters, mobile water, definitely. So what can get through it? Large or small molecules? Very small, because H bonding is going to hold the backbone together. It might have H bond there, might have an H bond there. And honestly, you're going to, today, I do not care whether it's parallel or anti-parallel. That is irrelevant. But I am going to have some sort of backbone interaction. And so it's held together pretty tightly. So if I told you glucose travels through a protein channel, you'd say yes or no? No, because one, I'm a liar. Lies are his. But why do you say no? Too big and uncharged. Exactly. Perfect. So what if I told you calcium, magnesium, chloride, sodium, potassium? Those could migrate through. True or false? Perfect. Okay. So I'm going to go on the assumption then that this is the bio portion is good for most of you. If it's not, let me know. And then also true confessions. My bio knowledge is minimal, so we'll have to solve things together if you have bio questions. But important to know, even numbers are hydrophobic, odds are hydrophilic. Are there really such words as lipophilic and lipophobic? Oh, it's not that the right diagram or left. Oh, why this one? Oh, it's just because it isn't that it prefers, it's just in a lipid environment. Can you have charged species? So if I put salt into oil, will it break into ions or will it stay as a crystal? Salt dissolves in oil, it's going to stay as a crystal. It will not dissolve in. The ions would rather stay with each other than go into an oil. So if I put something into oil, a lipid, charges don't want to exist, so it returns to this state. This proton gets transferred over there, and it ends up like this. But if I put it in a water environment, which can stabilize charge, then charges move over. Basically, like dissolves like. Is an amino acid able to, is it like, I don't know, split personality. Does it have its ion personality and its uncharged personality? Like this all is like. In an aqueous environment, it's going to go into its like form, like water. In its lipid environment, it's going into its lipid form. So it can take on two personalities, ion and completely uncharged. Hopefully it seems okay. All right. So now comes time to know a little bit more about the specific amino acids. So in this case, what would you predict for R3? More likely to be glutamic acid or valine? Okay, why is everybody voting glutamic acid? Charge. Okay, so seems reasonable. You want the charged species to be in the channel because the charged species is going to be more likely to be hydrophilic. Okay, so I totally agree. This makes sense. So then I want to ask one more thing, and that is, what if this was, let's say, a red blood cell? If I had a red blood cell, would it really matter whether it was a valine or a glutamic acid on it? Would that make any difference at all? Why? I don't believe you. Why would it matter? Why would it matter if my red blood cell had a glutamic acid sticking off it or valine sticking off of it? Main reason, if one's hydrophilic and one's hydrophobic, is that red blood cell, I forget, red blood cells exist in lipid or water environment. It exists in a water environment. So therefore, you want this surface to be water friendly so they better motility through the blood, makes sense. So naturally wants to have glutamic acid. If you replace the glutamic acid with a valine, valine is water friendly or wants to get away from the water? The valine wants to get away from the water, so therefore, does it force it to fold in a manner to now change its shape? Instead of being the normal red blood cell, does it pucker in? Like somebody mentioned, does it start looking like a sickle? As a sickle, it's the incorrect shape to take on O2, so it becomes an effective or ineffective oxygen transporter. Ineffective, so you get a condition known as anemia, sickle cell anemia. Perfect. So sickle cell anemia is exactly this, the changing from a glutamic acid to a valine. The reason I chose this is because, yeah, it's interesting here, but is it more interesting for those of you who studied sickle cell? And it also brings up something MCAT driven. Does the MCAT like to do this sort of thing? Take something you learn in one situation and apply it to a new situation. Are they guilty of such things? Very much so. And so these are the kind of things that if I can take something I remember from one area and apply it to a new situation, I'm set. Know the concept and reasoning. So one last thing on sickle cell, and I'll leave it alone. What causes sickle cell genetically? Is it a very complex mistake, or is it just one base, the third base? In the coding of glutamic acid and valine, it ends up the first two bases are identical, but the third base is different. So if I change just one base, what do they call that? I know there's a name for it, and I just can't remember. Nonsense? Okay, perfect. An overall point mutation. Perfect. Okay, so point mutation, at one point there's a change, changes the complete function of that protein. Okay, with that in mind then, how important is it to know things like which are charged, which are uncharged, which are hydrophobic, which are hydrophilic? Has that ever been important in folding? Absolutely essential. Environmental conditions dictate properties of all our compounds. So I'm going to come back to this in a second. So no need to screenshot. The only thing is this is going to disappear when I come back because I'm writing it here. And the future screen is going to be the same screen, but without this. So totally up to you if you want to screenshot it. Not essential. So I will click. Memorizing the amino acids, absolutely positively imperative you do this. Resort to flashcards if you need to, make lists. I don't know about you, but I'm a big fan of block memorization. So how many do that same thing? How many memorize things in blocks? Yeah, it's just easier. It's a whole idea. You can memorize a phone number, not because you memorize 7 individual numbers, but you memorize like the first 3 and the last 4. Although, how many don't even know phone numbers anymore? It's just they're all programmed in your phone and you just hit like person's name. Oh, actually, how many even know that your cell phone can be used to make phone calls? Totally forgot. There's a total generation gap here. I apologize. But yeah, I'm the phone generation. We actually use the phone app. So my phone has the telephone call app. It's pretty cool. Okay, so with that in mind, I'm going to block memorize. I'm going to block memorize all the hydrophobics to begin with, and it ends up I want to memorize them in a way that's systematically convenient for me. Here's what I'm hoping will happen. Gav, limp, p, I think. So help me out here. Are these the 3-letter codes for glycine, alanine, valine, leucine, isoleucine, methionine, uh, proline, and phenylalanine? And the 1-letter code you agree is always just the first letter. Nice and easy, no problem. Or have I made a mistake? And oh yeah, I want to pick up a message I sent yesterday. Will I be making mistakes during lecture that it is up to you to catch? Yes. Find my mistakes. That like find Waldo, forget Waldo, find my mistakes. There's going to be plenty. So what the F are you saying? Huh? You're saying phenylalanine because P has already been taken. Do we say F? So let's make it F. Perfect. Okay. So now am I set? And I've memorized them in a very specific way where I've gone from H to CH3 to 3 carbons, 4 carbons, 4 carbons, chain with a sulfur. So 3 carbons and a sulfur, a ring, and the massive one. So are these sequentially larger as we go? Yep. And does size matter in how proteins pack together? Massively. Weird question they had that I think is an excellent question. Once upon a time in a land far away called the previous MCAT, they may have asked, in a channel protein, which would be better for embedding into the cell membrane, alanine or phenylalanine? There's actually 4 choices. So you could eliminate the 2 hydrophilic ones. They were in the channel. But for the ones in the actual embedded into the cell membrane itself, the lipid, alanine or phenylalanine, which would be better? So how many agree they're both hydrophobic? So from a hydrophobic standpoint, they're both good. Weird question, but let me ask, and keep in mind, I'm asking this without giving you background information on the passage, which would have helped immensely. But let me ask you, which is better for a tree, a short root or a really deep root? Deep root, because you want trees to stay put or move around. You want them to stay put. Tell me about a channel protein. Are they migratory? Do they go in, they form, and they leave? Or do you want them to anchor in and be there the whole time? Are they a permanent or temporary? Permanent. Okay, so Sophie, you had that revelation. Tell me what revelation you had. You're absolutely right. It's phenylalanine. Why? Stronger root. It's a bigger structure. Plus, is benzene ring, the phenyl ring, is it planar? Sure. And do planar things go into the cell membrane easier than 3-dimensional things? It actually anchors in really nicely. So phenylalanine is the best of the hydrophobics to put into a channel protein to hold it in place. So how many would agree that makes total sense? Just it never was brought up. I'd never heard that ever until it popped up on the MCAT one time. And how many would agree that's really freaking cool? That's like one of those neat little oh yeahs. Yeah, it makes sense. You never think of it, but dang, it's pretty cool. The MCAT will do that to you. They're going to throw a few things. You have to know whatever. So I'm going to go with the, yeah, you can be upset like, no, I got to know their size too. Don't think of it that way. Just think of it kind of cool. Figure things out as you go. And yeah, you have to know a lot of things about amino acids because the number 1 topic tested on the MCAT is protein chemistry, amino acid chemistry. So, or biochemistry, I should say. Got to know that it's a benzene ring. Phenyl from the nomenclature in OChem, benzene ring. Yeah, in the real world connection, and I'm going to give you a totally honest confession here. I probably sound like I know way more than I actually know. I don't know very much. I just know how to make analogies. To me, the tree root concept makes so much sense that I can BS my way through this. The art of taking what you know and applying it to new situations is key on the MCAT. So the more analogies you have, the more you can make connections to other things. Absolutely critical. Okay, how many amino acids total do I need to memorize? Why 20? I thought there were 512 amino acids in the body. I remember some professor saying that when I was an undergrad. So interesting. You only want to learn 20. Why? So they are the 20 most common. There's definitely truth in that. Essential is what it defines an essential amino acid, by the way. Aleph, I like that. The 20 we code for. And I even want to qualify that. We code for 24, just 2 are just freaky weird. So we say we commonly code for 20. But what are essential amino acids? We have to take them from diet. Okay. Usually that's one of those things that professors don't go into a lot of detail on, but that's exactly what they are. Interesting that the essential amino acids they change pre-pubescent and post-pubescent. So I think that's maybe why they don't go into detail with those. But these 20 we commonly code for. So the 64 codons you have to memorize, what a few start, a few stops, and all the rest correlate. Okay. So I have 8 done so far. Here are my side chains for each one. Important to know the side chains. You gotta know your side chains. Truth of the matter, how many never had to distinguish leucine from isoleucine? Interesting thing, in my personal experience on the test, was given all the codon information. I didn't have to memorize anything, but it would definitely help if you could recognize quickly what has what. So how many learned that like one amino acid might have 4 codons? Like the first 2 make the difference and the last one is irrelevant. And then every now and then another set of like 2 amino acids will share something. And methionine is the stop or start codon. Methionine is actually the start codon. And silly way I remember it, methionine just doesn't get it. Methionine thinks the calendar starts in August. What does that mnemonic mean? So methionine's calendar begins in August. What's a start codon? Okay. You guys didn't answer fast enough, and you're the bio experts. I'm not. So a lot of times I'm flying by the seat of my pants when I start talking about bio. And so when I put stuff out there and nobody's responding, I went through like about 5-second panic, like, oh my gosh, do I have this wrong? Please don't let me have this wrong. I would have just said I did it on purpose and made you think your way through it. But yeah, August, start codon for methionine. Okay, so I'm good on this. I have these down pat. And the answer is no, don't memorize all 64 codons, but know a few. So start and stop maybe are worthwhile to know. Know that the start codon corresponds to methionine, meaning does every single protein in our body begin with methionine? I'm going to say that every protein in our body, the first amino acid is methionine. Is this true or false? And you know by my gender that I'm going to lie to you most of the time. Yep. So what happens if the synthesis, if the peptide sequencing starts, or when we translate it, we always start with methionine because it's start codon. Why is it not the first amino acid in every protein? So do we split it? Does it get cut? Sometimes the primer, you cut it off. And so when I go from the zymogen to the actual enzyme, does that happen actually pretty common? Post-translational editing, cleaving, all those things, perfect. Okay, so we're good on this. So back to memorization time. Again, I'm a big fan of block memorization. So I'm going to do that. Want to emphasize real quickly, why does proline get a star? All the other amino acids are kind of jealous. What does it mean that it is structurally important? It is cyclic. So is proline, excuse me, the one that has a link all the way around to the other side? So what happens then, because it's a cyclic structure, are rings easily folded and bent, or are they kind of rigid? They are rigid, which means if I told you my alpha helix had a proline in it, would you believe me? Nope. And then, Kimberly, what do you mean by a beta turn? Absolutely right. So forces it to make a sharp turn? Yep, exactly. So proline is the unique one that way. It causes all sorts of steric hindrance. So does it mess up protein folding? Yep. And and I want to follow up on both Melody's question and Meryl's follow up. You're absolutely right. Excellent question. And I am so happy when you guys do that to each other. Just like the positive reinforcement is essential. You're going to have enough negativity going through this process, and it's just going to happen. The positive really helps. Second thing is quit putting a question mark at the end of that. Totally true statement. You are absolutely positively true that proline is the one cyclic one and it causes trouble. Now, I want to ask you a follow-up question. Because it causes this sharp turn, do we usually pair it up with something? So if I see a proline in sequencing, is there a good chance you can tell me the amino acid right next to it? Glycine. Why glycine? Small. It doesn't get in the way. So if you tried to put a proline next to a phenylalanine, would the world explode? We'd try to fold on something crowded and it wouldn't work. So the proline forces a turn, glycine lives with it. Okay, perfect. Random information you need to know, but if I said, which of the following amino acids is going to mess up my protein sequencing, what is probably the best answer? So I sequenced this and I was only able to get 21 amino acids. It just, I couldn't sequence with any more accuracy. What is most likely the amino acid that screwed up my protein sequencing? Proline. Proline, because of steric hindrance, you can't unfold the protein well enough to cleave it. And it's not a major thing, but proline usually is the reason that sequencing starts to have a few issues. Okay, I feel pretty good about this. On the hydrophobic side, I'm gonna have some interesting names, and I apologize because they may sound offensive. Because there's, if you're serine or threonine, you might feel offended. But hey, accept who you are. You have an OH. Serine and threonine, S and T have not been taken, so we're good. CH2OH, CHOH. I'm going to add in a phrase here, and I want to qualify this. Let me, big picture. What is a triad? I know I've heard of it, but I'm not quite sure what a triad is. I think it's like, isn't it like a gang? No, it's just a group of three. Okay. So what exactly is a catalytic triad? Yeah. So the reason proline causes sequencing issues, let me give you an analogy. If I gave you a shoelace that was, let's say, 12 inches long, and I said, cut it at the 4-inch spot and 8-inch spot, but then I took it and I tied it in this massive knot, a knot on top of knot, top of knot, top of knot. So when you got it, it was just this balled up knot. Would you say it would be easier to try to put the scissors in at the 4-inch mark or to untie it first and cut it? Which would be an easier way for you to cut that shoelace at exactly the 4-inch and 8-inch mark? Untie it or leave it tied up? Untie it. Perfect. That's why we add things like urea, beta mercaptoethanol. These are the kind of things we add when we do sequencing. And so what happens then is we add these in to untie it so we can cut it. Proline does or does not untie very well, for lack of a better word. Proline straightens out, it does not, which means the Sanger's, oh my gosh, why am I drawing a blank on phenyl isothiocyanate? But I'm trying to think, I'll just use that, I'll use the chemical name. When you add it in, it has a hard time binding the peptide linkage between proline and the next amino acid. And so it doesn't, it takes a longer, it's a longer reaction. It just messes up our automated sequencers. Oh my gosh, Henshin was the wife. I'm sorry, I'm just drawing a blank. What is it Sanger's reagent for sequencing? It is, right? Phenyl isothiocyanate. I'm so sorry, I'm having a brain fart on it. Yeah, that's a compound. Edmund's reagent. Thank you. So sorry. So yeah, so Sanger's is the one that binds. Thank you. Gosh, it's so embarrassing. So anyway, back to this then. Catalytic triad. So I want to figure out what the heck that means, and I want you to teach me something. So when enzymes have whatever activity, how many times do you usually have like a cation of some sort, calcium, magnesium, iron, something in the core of that peptide? So enzyme, do you agree? A lot of times, is there a central metal that things ligate, they bind to? Sure. Okay. So the amino acids that interact with it, do you agree, have to be, number one, available to donate lone pairs. So they got to have lone pair activity. But number two, are active sites usually spacious or very crowded? Very crowded. So as a general rule, you're trying to force a bunch of things in an active site so that the substrate can barely fit, and therefore only one substrate can bind it, and it can carry out that reaction. You're trying to make it size specific to whatever substrate you ultimately want to bind and do whatever reaction to do. So here's what I think. I think serine or threonine, because they have an OH that can bind, that's going to be pretty good. But would it be better to use serine or threonine, and why? Serine, less steric hindrance, it's smaller. Because it's smaller, it's going to fit into the site more. So a catalytic triad is going to contain serine. Okay, when I say catalytic triad, is that a specific three, or is it the three that are key in different mechanisms we know, different pathways? So I want to see the bigger picture. So I'm going to list one type of catalytic triad, the one that we learned for, or at least I learned for chymotrypsin. It's like the first catalytic triad. But the key thing, you have to have a nucleophile, an acid, and a base. So typically, you protonate something to make a good leaving group, the nucleophile comes in and kicks it out, and then the base deprotonates it and gets it back to normal. So serine is going to be typically our nucleophile. Is there an outside chance that cysteine could substitute for it? If it wasn't busy being cross-linked, on rare occasions, could you have cysteine instead of serine? Cysteine is an S instead of an O. Yeah, you can. Okay, so fair enough. So I'm going to list this as the catalytic triad because serine is usually the nucleophile, but occasionally you can have a different one. Okay, the acidic amino acids. What are the two amino acids that end in the word acid? Dini. Perfect. Except they're not. They're A and G, aren't they? Isn't A and G? Have I messed this up? Because A is the first letter. Why is it not A? Dang it, alanine already took it. So I'll do the second letter. S, already taken. P, oh, there's already a fight over that one. So does it get stuck having to settle for a different letter? Gets a D. Glutamic acid, G is taken by glycine, L by leucine. U would work, but for whatever reason, they decided to give it an E. Okay, so you are aged when you study this, AGED. So this and this. Again, based purely on steric hindrance, which you think would be a more likely candidate for an active site, aspartic acid or glutamic acid? And I do like that. Somebody said Elmer's glue. I like it. Okay, so for this one, how many agree the smaller one is going to be better again, like you said? I'm going to put that in catalytic triad. However, and again, I want to qualify this, is there the potential that this other one could also be in maybe an obscure catalytic triad? Aspartic acid is probably going to be your most common, but it is potential to substitute cysteine for this. You could possibly substitute glutamic acid for that. Yeah, not often, but it could happen. The wannabe acidics, the ones that are just like this, no, the ones that have acidic properties, cysteine and tyrosine. This is what's kind of funky and weird. Cysteine C is good. Tyrosine T was already taken by threonine, so it gets a Y. But these two, why are they not actually acidic in the body? So why is cysteine? Because a cysteine residue has a pK around 8.4 for the side chain. Why do I not consider it acidic? And why does it get the green star? So tell me what I should know about cysteine. Disulfide linkages, disulfide bridges. Is that at all important to primary structure? Is that significant in primary structure? I lie to you. I make a lot of mistakes. So it's important in structure. What mistake did I make? The type of structure. So help me out real quick. What is primary structure? I should probably know this then. The primary structure of a protein is defined as the amino acid sequence. Amino acid 1, peptide linked to amino acid 2, amino acid 2, peptide linked to 3, and so forth. What is a secondary structure? Hydrogen bonding in the backbone specifically. If you look at the alpha helix, a secondary subunit, meaning it's secondary structure where the coiling is held together by an H bond. I'm going to get kind of emotional, spiritual, whatever you want to call it, but the hydrogen bond has to be linear. So just want to go off on a tangent real quick here. It's that if I have a lone pair like this, it has to interact in a very specific way. That's my hydrogen bond right there. Because it's linear, because you only get the right orientation of the orbitals when they're linear, do alpha helices have very specific dimensions? Any of you have a professor that made you memorize the number of amino acids per turn, the distance from one end to the other? Yep. So it sounds like you'd had to. 3.6 amino acids, 3.4 angstroms, 5.4 angstroms. These are the numbers that are popping up. How many definitely remember these numbers? Do these sound very familiar? Which means the H bond is so specific that it actually causes very specific structural features. When it's specific in the backbone, I'm going to refer to it then as secondary. So beta pleated sheets, alpha helices, those are secondary subunits. What's the difference between secondary and tertiary? Because tertiary can definitely be based on H bonding as well. Folding and side chain, exactly. Interactions of the side chains cause this, and they can be far away, meaning not physically, they have to be close enough to form a bond, but far away in the sequence. So is it possible that cysteine number 26 could form a disulfide linkage to cysteine number 114, way down the end of the chain? Yes, they can fold around. Is it likely that cysteine number 5 will form a disulfide linkage to cysteine number 8? Why not? Too close together, okay? If they are really, really close together like that, you get something known as a hairpin turn. But steric hindrance, you cause way too much stress in the structure, the folding. To have a disulfide linkage that's a benefit, for lack of a better word, they want to be far away. But how many have heard of a hairpin turn? For whatever reason, there was one passage on that. They were talking about lipozyme. They isolated from some chicken embryo and had this nearby linkage. So that's going to be an exception, but that's important to know. So cysteine can form disulfide linkages. When you memorize your information, I want you to do yourself a favor. Cysteine yet forms disulfide linkages. Does that mean if I want to untie my shoelace, if I want to do protein sequencing or any sort of experiment, do I have to disconnect? Do I have to break that disulfide linkage? So much so that is there actually an adjective to describe what type of electrophoresis it is? Native as opposed to reduced. So I want to take a second to get off on that tangent for a minute. But in order to go to this, do you agree? I had to go from cysteine SH to cysteine SH, which means, was it reduction or oxidation? Actually, you know what? Forgive me, I'm going to rewrite this whole thing because I'm drawing it so poorly, even I can't see it. Is that oxidation or reduction as I've drawn it in that direction? Why do you say oxidation? You're absolutely right. Why? Loss of electrons is the technical definition of oxidation. In OChem and biochem, I honestly don't see it. I'd have to look at oxidation state. Hydrogens. Fewer bonds to hydrogens is going to be the easier thing to recognize. So this is oxidation because loss of H's. You can also see it as loss of O's or gain of O's for oxidation. Heat will weaken other things, but not really disulfide. Disulfide, you need a reducing agent. You actually need something to break it down. So NADH can break it down biologically. Beta-mercaptoethanol can break it down in lab. So heat will break all sorts of other bonds, and it might eventually, if you have enough heat. But exactly, you want to add something that has, and I'll talk about that reducing agent in a second, but loss of H's. So this is known as hydrogenation or dehydrogenation. Dehydrogenation then is an oxidative process. Hydrogenation is a reductive process. Okay, so it's important to know cysteine crosslinks. One last thing I'm going to add in, and I seriously apologize because my palette is in the way. Even though it looks like there's lots of room to draw on the bottom, I did not plan this as well as I could have. So I'm going to start with beta-mercaptoethanol. I'm going to try to draw neatly. My wife has the most amazing penmanship in the world on her lectures. And I wondered how she did it because it made no sense. And it's because she uses a different program where you can adjust the pen. So I'm so self-conscious of my bad writing, so I apologize. Does the book say that? If you can send the page, because I think that's the whole point is it's not. It's a covalent bond, but it's tertiary or quaternary. And that worries me because that if it does say that, that's a typo. In the bio book says it. I don't know about the typos there, but in OChem, the OChem book, chapter 8, sure hope it doesn't. I hope that's it. Yeah, I've never heard that before, and the unfortunate thing, author is no longer around. Anyway, okay, so what's going to happen with this? Bear with me, but I'm going to make a connection there, and then break that bond, make a connection there, break that bond, make a connection there. So what happens, if you can indulge me, I'm going to erase things. So if you want to take a screenshot, do it now because I'm about to erase some things. But I end up with this when we're all said and done. That bond is now gone. That bond is now gone. That bond is now gone. And I put H back on that cysteine, H back on this cysteine, and the two beta-mercaptoethanol molecules now form a disulfide linkage. So we basically transfer H's from beta-mercaptoethanol back to cysteine and break that bond. Okay, and then the other compound that Kimberly mentioned, does this also provide two H's to be able to give back to break the disulfide linkage? Sure. The moral to the story that I want you to note, block memorization. Do not memorize cysteine disulfide linkage as a totally separate event from beta-mercaptoethanol. Memorize them together. So how many have definitely heard this concept that like you run an electrophoresis with native proteins and then you add a reducing agent and run it again and you end up getting different results? How many have definitely heard that when you took bio? Sure. Okay. That simply means you reduced it and turned it into a more, you break the disulfide linkage, got rid of tertiary structure, more flexible protein. Will it migrate more quickly or less quickly when you break the disulfide linkages? Migrates more quickly, less bumping into things. Make it more linear. It can slip through the gel much more easily than when it's a blob. Okay. Yeah, let me, so draw the structure of cysteine like this. Yeah, I'm going to do it. It's going to end up, because I'm going to have a very crowded screen in a second. I'll draw it and then I'm probably going to end up erasing it shortly after that. But I have my N terminal. I have my carboxyl terminal. I have my H with very specific stereochemistry. And I have the CH2SH like that. So if this is what you mean by drawing that structure. So does that seem okay? And then that's the one that SH turns into an SS bond. So that's, oh shoot, if I misinterpreted what you need on that one. Okay, well, let me erase everything then. So if it's okay, all this is going to go away so I can get some screen room. So 3, 2, 1. So something like that, you mean? Oh, dang it. Ah, sorry, not yet. Sorry, that was a tactical mistake. So does that work? Okay, and then when I reduce it, so I apologize for this, but I'm gonna, oh, didn't mean to do that. I meant to do that color. I'm gonna reduce it back down that way. And so you end up just losing those H's and making that connectivity. Okay, I'm gonna go ahead and erase if that's okay. Wait, okay. Yes, ask away. Yes, you're absolutely, yeah, you're right. And I'm just, that was just Everybody get what she was just saying? I was just being totally lazy. She is 1,000% correct. That is a correct structure. Absolutely, positively spot on. So why does it matter? Does that matter? What you just said. So Brooke, walk me through your thought process, because that was absolutely positively excellent what you did. So did you see some sort of mirror image that I've drawn as reflected? Yep. And if you have a mirror image, what happens to the chiral center? Stays the same or changes? Changes. Perfect. So my question to you then, Brooke is right on, because are amino acids either D or L, or do they have to specifically be L connected to L connected to L connected to L? L, L, L. So this, good call. That's a correct form. Couldn't try to draw that as a better line. But when we flip it around, the chiral center had to stay the same. But yes and no. So L is still cysteine, but you bring up the last of the really good points. So bear with me on this, but priority in OChem would be 1, 2, because of sulfur, 3 up here, 4 in front. So I would go like this, it's in front, so that would be an R. But in biochemistry, we prioritize 1, 2, 3, 4. So it would be H in front, so L. It's the one exception. So I want to go back to something I said yesterday real briefly. You're either a doctor or you lose. Meaning, if it's an R chiral center in OChem, it's D in biochem. If it's an S chiral center in OChem, it's an L. But is cysteine your exception? Is cysteine the one fluky one? Yep, because the priorities are different. In OChem, it's the highest atomic weight. Nitrogen beats carbon. Nitrogen beats carbon. Nitrogen beats hydrogen. So nitrogen's 1. H is the lightest. Carbon are the same. Which is heavier, O, O, or S? S is heavier, so that became priority 2 in OChem rules. So how many had a biochem professor that made a bigger deal about that? That cysteine is your freaky one, that D doesn't go with R and L doesn't go with S, that it's backwards. Yeah. So in general, for every sugar and every amino acid, it works out. Capital D refers to the chiral center of interest in whatever we're looking at. Amino acid, it's this one. What we learned as R and OChem, they define as capital D in biochem. For whatever reason, they decide to go with different letters. So it has to do with optical rotation, but they sign differently. So for every amino acid except cysteine, if it's an R chiral center in OChem, it's going to be a D in biochem. If it's an S chiral center in OChem, it's going to be an L in biochem. D goes with R, L goes with S for generally everything except, what's the lone exception here? Cysteine. Cysteine messes with the system because sulfur is a heavy atom, so it screws up the priorities. It's a one exception. So you're either a doctor, D goes with R, or you lose. L goes with S. Both of these are L, exactly. So these are both LRs. Okay, would they ever ask something like that on the MCAT though? Isn't that a little bit too detailed? They're not enantiomers. They're the same compound if they're the same chiral center. That was Brooke's point. That's what Brooke was saying. They have to be the same. We don't mix D and L in the same protein. They have to be a bunch of L's. But would they really ask this on the MCAT? Oh, yeah, by all means. And so, and actually, Melody, sorry, this is going to sound like a really weird targeted question, but it's just, I think you go to a school where somebody who I know teaches. Do you have T-ensign for biochem? Funny far off chance. No, I don't know if I had the right school. Yeah, a lot of the things she put on her test were things off the MCAT. She's one of those teachers. Gruber the same way, but they go out of their way. And so if you probably, she made a, I'm assuming made a big ordeal about cysteine being an exception. She never made a big ordeal until it showed up in the MCAT, and all of a sudden that was a big ordeal on her midterms. So just it's a good experience. Phenomenal teacher, wonderful, wonderful, really good teacher. So yeah, she never admits it, but she does her homework on it. She always reaches out once a year to find out just feedback of what was on it. So just kind of cool. No, cysteine is still L in the body. Cysteine is always L. Amino acids are L in our body, but it's an R instead of an S. Yeah. So my cysteiner is a ruler. Okay. But I'm gonna move on. Just I want to emphasize that, but there's something else I want to pop up. So I'm gonna get rid of this. So everything's gonna go in 5, 4, 3, 2, 1, gone. Want to just mention one extra little thing. There is another amino acid that I'm going to put in here called selenocysteine, which for whatever reason, I think it's SEL, and it's a U, I know for sure. How many had selenocysteine also as a weird exception added to your list? How many learned that as a 21st amino acid? It's a really weird codon, completely bizarre, that has to be one of the stop codons that follows, I think, phenylalanine. I forget exactly what these details are, but very, very rare. But once upon a time in an MCAT not far away, they talked about selenocysteine, which is selenium instead of sulfur, the atom right below it. And they talked about selenocysteine replacing serine in the catalytic triad. It was just some random mechanism, and they wanted you to know the following. The whole passage was to simply say this: is there any similarity in reactivity if the elements are in the same column in the periodic table? So in other words, is serine going to be similar to cysteine, similar to selenium? Yes. How many would freak out when they put selenocysteine in a passage because it's unfamiliar? Everybody does. The key thing, if that shows up in your future, just keep in mind O, S, and SE, same column, so they react in a similar way. A little bit longer bond, a little bit weaker bond might not be exactly as good a nucleophile or a base or whatever it's going in as. But selenocysteine was in a different catalytic triad and replaced serine. So just, and again, the cysteine exception for chirality and selenocysteine for coding, I'm doing these not because they're important, but because they were obscure, tiny little things on MCATs in the past. So one of those things, add it to your list of extraneous information that you probably will never be asked again in life, but somebody who took the MCAT in the past few years was asked that same question, and it freaked them out. Your job, don't freak out, just see it as the same periodic column. Okay, racing in 3, 2, 1, clear. Okay. A little bit longer chain. The reason I say this one doesn't matter, the pK is around 10. It's going to be really hard to have conditions where the body is at pH 10 or higher. So you'd never have to consider it in bio, but maybe in GChem. If they talk about putting something in a flask, then maybe you can titrate it, but by itself, no big deal. Okay, the wannabe glue acid, it's basically same thing here, except instead of an OH, it's an NH2. So it's an amide instead of a carboxylic acid. A is taken, S is taken, N, hey, N's not taken, cool. G is taken, L is taken, N just got taken. So what letter do we give glutamine? Q, okay? So when I memorize it in this order, I'm in pretty good shape. And let's see what I know. I know the ones that end in the word acid, the ones that are similar in structure, but they're amide. So I know 8. I know those 4 pretty easily. The alcoholics, the kind of alcoholics, but kind of acidics, the ones that don't know where they fit, That's 8 more, 16. I have 4 to go. What are my basic amino acids? Lies are his. Histidine, lysine, arginine. Perfect. So his lies are basic. How many have that down pat? We'll never forget it because just life gave you a free mnemonic. I love when that happens. So thank you, life. Exactly. They just flat out tell you. So now you know. Histidine. Absolutely imperative that I know which nitrogen is the important nitrogen. Which one is it? There's 2 nitrogens to choose from. Which one is the catalytic nitrogen? Oh, why did I put it want to be acidic? Because phenols have pKs around 10. Alcohols are usually around 15. So because we think of phenol groups as being a little bit on the acidic side. So, and this is just, that's how I categorized it. And it just was easy for me to block it that way for memorization. And what, arginine is not A? Also, is lysine L. So haven't quite gotten to that yet, but yeah, definitely have errors there. So we'll hopefully fix those. Let's get the histidine down pat. When histidine takes on an H, because it acts like a base, does it do that? I can't remember. Does it put both on the same side? Is that the way it looks or no? Does that look right to you? It is not, because did it just lose its aromaticity? Whereas over here, that pi bond, and lone pair here, can they all be shared? So yeah, so aromatic, for whatever reason, they just describe, histidine gets left out, and I don't know why. Most textbooks will tell you phenylalanine with a benzene ring, tyrosine with a phenol, benzene with an OH, and then tryptophan, which is going to have over here, all have that 6-membered ring with the 6 electrons in it. They typically consider aromatic. For whatever reason, although histidine is definitely also aromatic, they just don't include it. Can't tell you why, don't know why it doesn't qualify and why they don't put it in the group, but they just don't. So, if it's basically buried in the reading, just sort of, I'm going with paralleling what most textbooks said. I can't give you an answer why they decide that the other 3 are considered aromatic: phenylalanine, tyrosine, and tryptophan, and why they exclude histidine. But I think they just want to make histidine more important. Okay, I'm going to erase all my noise and say, as a result, then, can't go on the nitrogen I said. So the important one is that one. That is your so-called catalytic nitrogen. This is the one that's going to donate its lone pair. The other one, it's tied up in the aromatic ring, so that's the one that's going to be active. So histidine's also in the catalytic triad. You need a nucleophile, an acid, and a base. You have 3 bases to choose from. This one has a pK closest to physiological pH, so it's the most common choice. Histidine's pretty much in every mechanism. Aspartic acid, glutamic acid, a little bit smaller, so a little bit better choice. Serine, smaller than cysteine or selenocysteine, so better choice. But every now and then, a certain enzymes, catalytic triad, its nucleophile, acid, and base, might include something a little out of the norm, but usually it's those 3. So how many had to learn just the concept of catalytic triad? 3 amino acids, one that's a base, one that's an acid, and one's a nucleophile. So was that something that popped up for any of you in your pathway in first semester or first quarter biochem? Okay, so yes, same, no. Yeah, it's one of those, it's so weird. Some professors are totally into it. And I think it's a personality thing more than anything. So some have never heard of it before, some have. I had never heard of it in my life. Didn't pop up in my biochem class. It's popped up in the MCAT a couple of times. And it just simply means the pathway or the mechanism we deal with has a nucleophile, an acid, and a base. So for whatever reason, you protonate it first, the substrate, the nucleophile comes and attacks it, forms a new bond, and then the base deprotonates it at the end. So how many have learned that in OChem? A lot of times there's a thing where you protonate the leaving group, nucleophile comes in and displaces it, and then you deprotonate it to get it back to neutral. Is that a pretty typical 3-step OChem pathway? This is a 3-step biochem pathway. It is a nucleophile, so you protonate, make a better leaving group on the substrate. Nucleophile comes in and attacks it, and you protonate, and it goes back to release substrate now as product, and the free enzyme again. Okay, last thing I want to add. Oh, I got to make some corrections. So, yep, you're absolutely right. This was K. There's my chain for it. And this is R. Absolutely right. And there's the side chain for it. The last thing, random, and I just find it so damn funny. I'm just going to leave the writing up there. But how many had a professor that took the time to tell you that tryptophan is really common, or turkey has a lot of tryptophan in it? And how many agree, what an absolutely useless piece of information? I don't know about you, but I remember sitting there thinking, why? Supposedly it makes you sleepy after Thanksgiving, they tell you that, but with all the important stuff to learn, it's such an obscure thing, but I just figured, you know what, might as be a smart ass and toss it in there. So what's a 1-letter code for tryptophan? Tryptophan T is already taken, A is already taken, and P is already taken. So tryptophan, tryptophan is double woo. Wow, that's tryptophan? Perfect. Benzene ring, again, in a tryptophan. Okay, want to just mention real quickly why I would ever care about tryptophan. For this one, how many know what, like, just out of curiosity, how many have ever heard of something like a catecholamine? Is that a category? Yeah, so somebody's asking pacing question. Again, this is probably going to be pushing all the way to 12. I'm so sorry about that. It's just, it just getting a lot of the stuff down pat because you didn't see it in previous lectures. Got to make sure for that. But for tryptophan, I'm going to mention it turns into some sort of compound, but tyrosine has an OH. How many know what a catecholamine is? An amine with 2 OHs on it, on the benzene ring? Catechol is a phenol, but with a second OH. How many learn catecholamines are things like norepinephrine, epinephrine, neurotransmitters? So amino acids, one of the things that maybe shows up in your biochem classes, can we use amino acids as starting material in making other compounds? So for instance, tryptophan can decarboxylate and turn into serotonin. There's a few other steps. Tyrosine can decarboxylate and turn into catecholamines. So a lot of amino acids, when they decarboxylate, lose the CO2, turn into useful amines. So a lot of drugs, a lot of neuro compounds are amines. A lot of neuro drugs, I should say, are amines. Okay, want to get back to the previous thing and then want to go through with synthesis. So this is going to go away in 3, 2, 1. Okay, I lied. Tyrosine, by the way, and I moved it back to the middle for a reason. How many were taught when they put the categories of amino acids, they didn't bother telling you whether it was hydrophilic or hydrophobic. They just said aromatic. It's because there's a controversy. Some textbooks, older ones, typically will tell you tyrosine is hydrophilic because of the OH. Newer textbooks will tell you it's hydrophobic because it's definitely found in hydrophobic pockets. It ends up, it is both. It's amphipathic. It will be what you need it to be. You put it in a hydrophilic environment, OH will become important. Put in a hydrophobic environment, benzene ring. Typically, phenols are relatively insoluble in water, but they have some slight solubility. So it's open to interpretation. At this point, I'm going to put it in the middle because it can go either way. But if you were bothered, how many were bothered that I put it under hydrophilic because you learned it's hydrophobic? I wouldn't even notice. But some professors will put it hydrophobic, some put it hydrophilic. It can be found in both locations. You can find it in hydrophilic spots. You can also find it in hydrophobic spots. So it could be found on the active site of a hydrophilic charged molecule, or it can also be buried in a hydrophobic pocket. So it's a dual citizen. It depends on environment. Exactly. Everybody just, I mean, read that. Depends on environment. All right, welcome. Okay, back to this. Just a few quick questions. You need to go through this incredibly fast now. Threonine, odd or even number? You have 5 seconds. Yeah, so why is the book different than lecture? Mostly because, and this is going to sound terrible, but if I'm being completely honest, it's because I have learned, I adjust my lectures every single time. And that's because based on what I learned from previous MCATs, and because previous MCATs made a little bit bigger ordeal about that, I've adapted my lectures. So basically, there's some things in my lecture that have been added literally last year or two. That book was last updated in 2018 because honestly, we don't sell or make enough books. So reality is we reprint each book about every 4 years. So it's just honestly, the book is slightly out of date compared to lecture. So yeah, and I sincerely apologize. Most things are going to be no big deal, but there are a few things like that. Like for instance, you will not find selenocysteine in the book at this point. It will be in the next time I write it up, like it's already written in for the new printing, but simply because that showed up in MCAT real recently and I need to incorporate it. And so there's lecture is always going to be the more current. And yes, R13. Perfect. Phenylalanine, hydrophobic, hydrophilic. Hydrophobic, so therefore you're going to find it in the lipid bilayer. Perfect, even number. Proline, proline would be good or bad in a channel. Terrible in the channel. Would it be kind of useful at the entrance of a channel? Would it be good to make the channel wide berth so things can come in? So exactly what Melody just wrote. It'd be phenomenal at the bottom of a channel as you exit a channel, but terrible within the channel. So how many are starting to get this? How many just like you can get this really quickly? So what do you want? If I want to shuttle things in and out, which pathway would you want? Would you want a nice straight pathway? Or would it actually be better to have this crooked pathway to get through? So would it better have a channel protein that looked, I'm trying to uncolor this, which is not going well. But which channel is going to be better, a straight channel or a meandering channel? Why straight? Stay on the straight and narrow. Easier to get through a straight channel. It's already hard enough to go through this environment. So if you make it go around, if you have a proline that causes a bend or a turn like this, you mess it up. It would bend. So tell me which is a better thing, to have a protein that goes like that or a protein that goes like this. Because a protein extends. There's still an R6, R7, and R8, et cetera. But if I have a proline here, I can get an abrupt change. So I have much better pathway to get in. Here, a little bit harder to get in. Yeah, exactly. Perfect. It's a funnel. Funnels are better when they're big than short and straight. Okay. Oh, you're so welcome. The big thing, and the thing I'm going to click to something new from this point on, but before I move on, how many, yeah, you know cell bio pretty well, but more importantly, the phenylalanine was a new piece of information, possibly the proline on the channel, all that. How many have never studied that before, but now you can deduce it? It makes more sense. Yep, funnels it in. This is a thing I really hope more than anything you're getting out of lecture. You can memorize stuff on your own. You can go Anki all day long. It's now that you know it, can you make decisions with it? The MCAT is about making that decision. Proline is better here than it is here. That's the kind of thing you have to make sense. Phenylalanine is good here because it anchors in better than alanine. Hydrophilics, good here because they help ions move across. So going one step further, which would be better on the inside? glutamic acid or aspartic acid? Both will work. They're both hydrophobic or philic, excuse me, but one is going to be better than the other. Why? Why aspartic? Smaller. Melanie nailed it. Less dairy hindrance, less crowding, less hydrophobic, less CH2 in the channel. Absolutely perfect. So when you start applying the things you learned somewhere else to this sort of question, that's where it's really going to benefit you. Sorry, I'm getting all geeky excited, so forgive me for that. But, oh, sorry. Hopefully you screenshotted because all that writing's gone. But other way that things show up then. Yeah, proteins, those are really big. We study the crap out of them, but also synthesis. I'm going to pat myself on the back, so forgive me for a moment here, but about 4 or 5 years ago, when I was putting together this lecture, decided to add in just a synthesis. There's lots of things. Like I mentioned, serotonin comes from tryptophan. Serine is used in a whole bunch of different synthesis pathways, tyrosine as well. It ends up, put this in here, and the very next MCAT it was on, I felt incredibly good, like yay me, until about a year later, serotonin synthesis was on there. Then the acetylcholine synthesis. Basically, they took this concept, any amino acid can be turned into something else. So that said, I'm going to go through this pathway, but I want you to see it always as a big picture. Don't memorize exactly tyrosine going to adrenaline. Know why it matters. So the first thing you need to know about biochem. Biochem is magic. In OChem, we had to know exact mechanisms, how things happen, pathways. In biochem, what's the answer? Enzymes perform magic. This enzyme can put it specifically at one spot. So do you agree there's 4 different spots that OH could go? If you remember, lone pair goes in, so because of resonance, it's going to be an ortho para director. Para is already taken, so ortho. So I'm down to 2 spots. Does it matter whether it goes to one spot or the other? Would that change the chirality? So if the OH here or here, does it really make a difference? Nope, exact same structure. So with OH is on the left side or the right side, that's not a chiral center, not a chiral center, and this didn't change priority, stay the same. So it's going to do ortho position, 1 away rather than 2, but it can do either one. Okay, so I'm going to say magic makes this happen. Would you call this an oxidation, a reduction? Which one? This is a stereospecific oxidation, meaning I get a stereospecific center, or is this just a plain oxidation? Now I'm going to be a little more anal about it. Stereospecific oxidation? No. No new chiral center. So hopefully it seems okay. Before I do that, I click too fast, but is L-dopa an amino acid? That was one of their questions. What makes something amino acid? To be an amino acid, you need an amino, an acid, and an R group. Does it qualify? Does it have an amino, a carboxyl, and an R group? Sure does. Meaning, this is an amino acid. Why aren't we memorizing it? Why aren't we making it part of that 20 or 21 or 22, whatever number you want to say? It's not, I mean, it is true. I don't take it through diet. We do make it. We don't digest it. It's temporary. It's an intermediate in this process, precursor to something else I need. I don't code for it. I just have no code for it. I can only get it by converting an amino acid I code for. So when I mentioned there's over 500 amino acids in the body, is this one of those other 480? Sure. Okay. What type of reaction is this next reaction when it converts from L-dopa? And shouldn't it be L-dopamine? I think I messed that up. It should be L, shouldn't it? Perfect. So it is decarboxylation. I'll write it in a second. But is it L-dopamine or no? Chiral center is gone. There is no L. So this is decarboxylation. Would they ever really want me to know name reactions? Oh, no. I can't write the N. How many know that it's decarboxylation and don't mistake it as being, I'll fit it in, perfect. So how many know name reactions? Yeah, so excellent. So somebody mentioned, confused about where the extra OH came from? It came from magic. This O oxidized right here. So this used to have an H, and O magically got inserted into that bond and made it an OH. So, and I am so on the same page with you. Would you agree, what the, put in profanity of choice? You agree, in OChem, if I just said an O magically inserted into a carbon-hydrogen bond, you go, that's insane. Biochem, we don't care. We just notice the differences. So it's just weird. So are you by nature an O chemist that wants to know how did that happen mechanistically, like I am? Yeah. Okay. And by the way, I'm having that conversation with a private messenger, so I apologize. Yeah. So we're going to define a chiral center as that. Oh, you don't like Orgo? Oh, okay. I'm moving on then, because that's painful and hurtful. Like, you could call me names, but don't do that. I'm just kidding. So for this one, yeah, there's no longer 4 unique things. It has 1, 2, 3, 4, 2 H's, identical things. So no chiral center. Loss of chiral center. Okay, we move on. Next step. Ooh, is it more magic? So whereas this was an oxidation, is the next one a stereospecific oxidation? Yeah, and then also Jonathan pointed out the lack of the L was because we lacked a chiral center. We had to drop the L because it's no longer chiral. This is still oxidation, but this is stereospecific oxidation. What does that mean, stereospecific oxidation? Now that becomes a, I guess, a more difficult term to comprehend. Is it important that I get the right chiral center, or does it really matter? If it's RS, does it really make a difference? Yep, we created or changed in a very specific way. We didn't get in an enantiomeric mixture, we didn't get a racemic mixture. We got one specific chirality. Is biochemistry specific? Is it chiral specific? Yes. Our enzymes are very specific. Our sugars are very specific, meaning all our chirality has to be specific. So is this actually really critical that it is only in back and not in front? You bet. Last step. Question. Is this N connected to this C? Perfect. Which do you think is the nucleophile, CH3 or N? N. Perfect. Which means this, I'm going to be a little more specific, has to have a leaving group. Leaving groups are better when they're tiny or massive. Which makes a really good leaving group, a small or large compound? Think steric hindrance? You want small nucleophiles and you want massive leaving groups. You want a small thing to come in and kick out a big thing so that it can make a better bond. So typically, you enlarge, you protonate or build or enlarge a leaving group and try to make nucleophiles smaller. So big can help stabilize the charge, definitely true. So this is a primary amine nucleophile, and it is going to attack, that lone pair is going to attack that carbon, and kick that out, and end up methylating it. Oop, didn't mean to do that, I meant to do that in red. So this last step is a methylation. And I want to stop for just a moment and ask you, how many are sitting there thinking, why am I wasting my time naming every single reaction, specifying stereospecific, what type of nucleophile? Are these the type of questions? Remember, who's taking the MCAT, are these the pesky little questions they like to ask? Oh, that is, Lydia, that is so, you're so psychic. We were on the exact same page. It would be halide if I'm working in an OChem lab. Halide in my body might be kind of toxic. So usually it's a massive ester. It's almost always an O with some massive group. But if you say halide, you're thinking like an O chemist and you're still right where you need to be. But it's usually O with a massive group. So ester leading groups are very, very typical. But for anybody who's taking the MCAT, or even if you've only like, do you remember them asking for names of types of reactions? What is happening in step 4? What do you predict to be the reactant that we use in step 5 or something like that? So for anybody who's taking the MCAT, did you get a pathway one like this? And did they ask annoying questions like name that reaction about a Carl Center? So basically, you want to know what questions they asked? Every single question I just asked, but now with 4 choices. So what kind of reaction is this? Would be the following reaction could be classified as carboxylation, decarboxylation, stereospecific oxidation, nucleophilic substitution. In this case, the reaction can best be classified by having nitrogen acting as an electrophile with carbon as electrophile, nucleophile, electrophile, electrophile, nucleophile, 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 those sorts of things. So literally every question I just asked turned into multiple choice. That's how MCAT questions like to go. So is it okay to move on from this screen? Okay, moving on in 3, 2, 1. Now I like to mess with you. Yes, everybody read Stephanie's comment right there. The take-home message, see the big picture, name the reactions, the details of the mechanism. The only one I went to any detail was the SN2 reaction at the very bottom, where the primary amine, a primary nucleophile, attacked a primary or methyl with a leaving group. So the only mechanism that I drew, the only arrow pushing I did on the whole dang thing, would you agree, was the SN2 reaction in the very last step? Other than that, perfect. Okay, for this one, we just went through all this amino acid stuff, and how many agree I've just thrown a bizarre what the blank type of question? So let me just tell you, yes, this is based on a real question. No, the answer choices weren't this hard. This was me being exceptionally mean because I want to use it as a teaching tool. But are there amino acids in this compound? I don't know. Every amino acid has an amine and an acid, so can I at least start with this one being my acid? So there's my acid. So I want to find the backbone. So if that's my acid, alpha and N, can I say that that's my first, or I should say last amino acid? So I'm going to agree that this one right here is the carboxyl terminal, N terminal, and the carbon. And then one more over here. We can do it in slightly different color, carbon, this, and nitrogen. So I think I'm on to something. If I can just simply make this contain there, oop, add column my part. And maybe make this one contain that. And then the rest of the chain down here. So we got a methionine and valine. I'm liking the guesses so far. I don't know yet. So let me rotate that up. And now there's officially too much writing. So I'm going to get rid of my writing and just focus on this piece right here. So that side chain, is that the side chain of valine? Is valine a C with two CH3s, like a V. So that's a valine, definitely true. Okay, what else then? Methionine and cysteine, which one has a CH2 and an S, possibly an H on it? Methionine couldn't form it. This one has to be that. So cysteine. How many would agree this is a really tough question? I mean, would you categorize this one as, damn, this was hard? Okay, what if the test writer wasn't a mean, evil person like me and somebody nicer, and they might have said things like phenylalanine and leucine, valine and isoleucine, valine and cysteine, something like that? In other words, if there was only one cysteine in here to choose from, would have been a much easier question. So would the answer choices help you? Okay, so relax a little bit in that what I pilfered and modified this from, only one of the four answer choices contained a sulfur containing molecule. There was only one cysteine out of all the choices. So there was no methionine and one cysteine. So for what it's worth, I made a harder question because I really want to emphasize the learning aspect of it. But if you're freaked out like, damn, that's overkill, yes, that's me being mean to emphasize this. Okay, so onward I'm going to march. Beta-lactams, this category of compounds we just did. Oh, the side chain. So if I look at this compound, actually the structure is going to kick in here. So why is this a cysteine residue right there? Methionine is CH2, CH2, SCH3. Cysteine is CH2, SH. It's just that part. Methionine is too long. Yeah, and then exactly what Melody said. Hopefully seems okay. But important, those are the things to recognize. And then again, also, and the main reason is just, if you can think here in this instance, you'll be smoother down the road. Beta-lactam, nomenclature. What kind of compound is that if you have a carbonyl with an OR group? Ester. If it's in a ring, though, we call it a lactone. Not sure where that nomenclature comes from. This is called an amide. If it's cyclic, what do we call it? Lactam. Perfect. So that means this functional group here is a lactam. It has a carbonyl to lose it when it's information and big word intensive. Yep, I'm just gone. This is a totally true statement taken out of a bio book that doesn't mean squat to me. I just know this thing explodes and binds an enzyme that doesn't allow a linkage. See the big picture. That's the best message. Okay, from memory. I want you to get this question. I'll give you about 30 seconds. Okay, how many without seeing the structure are able to get it? You will have the structure given to you, but how many agree ring strain? Definitely form of a ring, lots of ring strain. They will provide the structure by all means. Okay. So I want you to do it without it from memory, but definitely a ring strain. What is a unit of unsaturation? Again, this is one of those things that would have been covered in an earlier lecture. But unit of unsaturation is a pi bond or a ring. So for instance, I'd say that's unsaturated. That's saturated. Have I said my words right or no? Nope, completely backwards. Saturated with hydrogens. So this is saturated. That would be an unsaturated fat or unsaturated alkene. But also, those are both unsaturated, meaning they don't have the maximum number of H's for the carbons. So pi bond or a ring. So let's count. One ring, two rings, pi bond, pi bond, pi bond. So does this have at least 5 as drawn? Is there a plus charge on a nitrogen, or all the nitrogens tied up in resonance? All nitrogens tied up in resonance? They cannot. They can't become positive, so C is your best answer. Lone pairs are all tied up. So beta-lactam has ring strain, you bet. Beta-lactam has 2 rings, at least 2 pi bonds. Check. And all of them have 3 bonds, so they carry no charge, and they are sharing with resonance. Okay. So moving on from structure, gonna just do quick synthesis and then, okay. Yep, pi bond is in a double or triple bond, exactly. So in a double bond, I have 1 unit of saturation. In a triple bond, I have 2 units of saturation. So exactly, so individual pi bonds, every one of them counts as a unit of saturation. Strecker synthesis, oh, you're welcome. Synthesis-wise, and this is just one of those things generically I want you to think about in terms of synthesis. For synthesis, we need to think about what we still need to add. So how many agree for an amino acid, that's what I'm trying to make. Amino acid has a central carbon that contains an amino terminal, a carboxyl terminal, an R group, and an H. And so I'm only going to go over Strecker. Gabriel is going to be one of the ones you run into in your homework. It's going to be the same concept. You just have to keep track of what you're adding. So far, I have an R and an H on there. So I have my R and I have my H. So how many steps do I need to do minimum in this synthesis would you predict? So it seems kind of a logic thing. At least 2, exactly. I need to add an N, I need to add a carbon. And then is there pretty much always a cleanup step at the end? Acid, if you had base before, base if you had acid, just get it back to neutral. So I'm going to do it in the following way. Which is a better nucleophile typically, nitrogen compounds or carbon compounds? Nitrogen. This is an electrophile, so I'm going to add a nitrogen to go in. And so when we add ammonia, it's going to go into something called an amine. An imine is very much like a carbonyl, double bond to an electronegative atom, but at least I put it on here. It's not in the form I want it, but I can get it into that form. So I add an amine, my nitrogen's been added. Okay, I now have to add a carbon. The carbon nucleophile that we know of is cyano group. So if I want a carbon to attack, we have this minus charge here. Attacks. When it does this, it pushes up to there. So I have a nitrogen with a bond. And I'll put the CN group on. So I now have all the things I need. I have the original R, the original H. I've added an N. I've added a carbon. Is this an amino acid? Not yet. Okay. So I want to just show you 3 reactions. And I want you to tell me shoot, that last one. Forgive me. No one tell me if you've ever seen this before. Have you ever seen a bond broken between a carbonyl and an O? Does that ever happen? Sure, it's called hydrolysis. We do with water. I put an OH here, put an H there. So I want to make a point here. Is the heteroatom, is that atom always getting the H? They'll get the H here, they'll get the H here. So if I do this, I'm going to put an H, an H, and an H. Let's see, if it's a single H, I said an OH over here. If it's 2 H's, I said an O. What kind of reaction do you lyse or break a bond using water? Okay, sorry, I'm behind on the chat box. So yeah, an imine, the distinguishing factor is the double bond to the end. I'm so sorry, I just never saw your question, Alex, because I just have a limited chat box. My sincere apologies. But yeah, a double bond to an N is called an imine. Triple bond to an N is kind of nitrile or cyano group. So amine, imine, cyano, or nitrile. Arginine has an imine bond in it, definitely. Okay, but what do you call this bond, or this breaking, this lysis of a bond using water? What kind of reaction breaks a bond with water? I think it's water lysis, or is it hydrolysis? Hydrolysis. So is hydrolysis something that's incredibly common in biochem? You undergo a lot of hydrolysis of various bonds. So again, because we do it in biochem, do I worry about a mechanism or do I worry about magic? What carries it out more often, magic or mechanisms? Magic. So I'm going to have my magic water line. 3 bonds, H, H, and an OH, and an O. So magic is going to cleave that. I'm going to add water to hydrolyze it. I'm going to get rid of these 3 in just a second, so hang on. So if you want a screenshot, now is your moment. 3, 2, 1. I want to leave the upper thing up there, so sorry, I'm erasing one at a time. But I undergo the magic water line, hydrolysis. H's go to the leaving group. So I have 3 H's on N, I have O's there. I'm left with this compound, the amino acid. How many are okay with this process? Add an N, check. Add a C, check. Hydrolyze it to get to the compound you need. The details of how acidic, how basic, I'm not going to worry about that. I'm just going to worry about adding an N, adding a C, hydrolyzing, get it down to what you want. Okay. The magic water line, because hydrolysis is going to be somewhat prevalent in your experience on the MCAT, just be able to draw a line, put H's on the leaving group, put O on the carbon. Oh, that is an excellent question. I'm going to say they are sometimes formulated like this. So might be a slight like mechanism one, but usually it's what are you going to do? How are you going to make this thing? Okay. Your job, complicate or simplify? You guys own it. You guys freaking own this. I'm so impressed. Simplify it as much as possible. So you've recognized amino acid side chains. Forget that. I'm going to go with math. Strecker adds 1 carbon, and valine has 5 carbons total. So side chain 1, 2, 3, the alpha carbon and that carbon. So what plus 1 equals 5? SN2 is not, SN2 has to be at an sp3 carbon. So no, because you're attacking carbonyl, you're attacking at an sp2 center, not an sp3 center. So SN2, you're attacking sp3. So this is actually just carbonyl substitution. So it's a real picky detail, but no. Same thing, nucleophile still coming in, but it's not kicking out a leaving group right away. It's breaking a pi bond, then kicking out a leaving group. So in exchange, what plus 1 equals 5? Oh, for this one, what starting material? So in this one, I don't know. I have no idea what I'm starting with. That's what I'm trying to figure out on this one. But what I know is I know what I want to get. I want to get valine. And I know valine has 5 carbons. And I haven't memorized, oh no, what do we have in the flask? We have one of these 4 choices. So do you read a starting reagent is what you start with in your flask. So it's basically asking, what do you put in the flask to start out with if you're going to do a Strecker synthesis to make this? So it comes down to, I want to make this compound and I want to use this procedure. So I know that this is the target compound of 5, and I know that this procedure adds 1. So the thing I start out with must have how many carbons? Perfect, exactly. Has to have 4. So that means whatever we start out with the flask has to be a 4-carbon compound. Which of those choices is 4 carbons? Perfect, choice C. So 2 carbons, 3 carbons, 3 plus 1 is 4, 4 plus 1 is 5. Also, the way Tiffany did it, just take the final product, get rid of the cyano, get rid of the nitro, and make that. This is 1, 2, 3 carbons in a row, so it's propanol with a methyl on 2. So perfect. How many are okay with the simplified approach? How many are fine with recognizing that this adds an imine and a cyano group? An ammonia to form an imine, cyano group to form the carbon. So you're only adding 1 carbon total. If you want 5, you start with 4. If you wanted 12, you start with 11. Keep things as simple as you possibly can. Again, Gabriel synthesis is the other one. So in 2015, they added Gabriel and they added Strecker. Yeah, and it's just a matter of exposure. And homework is going to give you a Strecker and a Gabriel, but I want you to do the Gabriel without any background. So why not B? How many carbons in propanol? 3 carbons. So I would be missing this group right here if I just did 3 carbons. And so my amino acid would have been an N up here, a carbonyl up here, and just that. So wrong side chain. So does that seem reasonable to you that this one is missing that CH3 that you need to make it valine? So you have to have this whole group for valine plus this carbon. Yeah, so we're missing the carbonyl carbon from the carboxyl terminal. This is just the starting one. So 3 of the backbone plus the 4th. Okay. Titration curves. I'm going to kind of blow through this to the background and then get into the details of this. Oh, it's such an excellent question. I want feedback from people who take the MCAT to confirm this, but when I took the MCAT, I didn't feel like I needed to know very much OChem nomenclature at all. Yeah, so yeah, this is actually a 10-minute break. Yeah, let me just answer that question and I'll take a like 5 or so. But OChem nomenclature, don't stress about it. You'll be able to figure it out as you go. The only time it ever popped up for me was when they were too lazy to draw structures out. They draw names, but most of the time they gave structures. I felt I didn't have to do very much nomenclature. I try to force it into answer choices and questions every now and then, but by and large, it's not like that one is about the upper limit of how they'll push it. But okay, right now, according to mine, 11:02, can we get back at 11:08? So a little over 5 minutes. So okay, I'm gonna go off mic for a second, and I'll be back in 5 minutes. So isoelectric point. This pretty much is the last thing, but it's usually a long one. Okay, so potty break, and we'll be back in 5. How many learned that PK1 was there, PK2 was here, excess titrant? You just over titrated. Does that sound familiar? Okay, and then how many learn that the point in between, because this is a symmetric curve, that the pH at this point is an average of PK1 plus PK2 over 2. Does that sound familiar or seem okay? And I'm going to go out on a limb and tell you this one, and because of dilution factor, it's not perfectly true. So I'm going to put a approximate P2 plus pH of titrant over 2. So let me just make this a little more legible. But how many have definitely learned the point in between is an average of the 2? The point in between is an average of the 2. Hopefully that seems familiar. Okay, I'm going to take advantage of this by now applying it specifically to an amino acid. So this is a key thing that we're going to use in both GChem and biochem. So I'm going to erase this. It's going to be gone in 3, 2, 1, and excuse me, sorry. Oh, sorry about that. Okay, so let's consider just plain old run-of-the-mill amino acid. I pick alanine because it's easiest to draw the side chain. But overall, when fully protonated, it is +1. This point it's 0, and this point it's -1. So what defines the isoelectric point? What is the definition of the isoelectric point? It's where the zwitterion is in highest concentration. It's where it has 0 net charge. So I put it in electrophoresis, electric field, won't migrate. If I try to add it to a charge column, it'll just elute, it won't bind. So it's a point of 0 charge. So this right here is my zwitterion. I'll just put zwit. And the PI is an average of, it figures I put it right in the middle. So let me get rid of that. So that's my 0. There's my -1. That's my Zwitterion. And isoelectric point, again, is an average of the two pKs that surround that. But I want to just bring something up. And that is, if it starts at +1, would it make sense that it's only going to take one deprotonation to make it neutral? Does that seem reasonable to you? Okay, so what if it was +6? How many times do I need to deprotonate it? 6. Perfect. If it started at +84, you have to deprotonate it 84 times. So is it reasonable to say that if I know this number, I automatically know that number? Are those always going to be the same number? Whatever charge it starts out with, is that the number of times you'll need to deprotonate it to make it neutral? Yes. That's going to be our shortcut. So I'm going to think about it for a moment then. If it just has a carboxyl and amino terminal, carboxyl is going to be protonated neutral at low pH, amino is going to be +1. So anything that has an inert side chain is just going to be an average of pK1 and pK2 all the time. Okay, I'm about to click. So if you're screenshotting, 3, 2, 1, clicking. For glutamic acid, aspartic acid, tyrosine, and cysteine by themselves, no longer in a protein, but single amino acids in a flask, I'm going to pick aspartic acid, again, short chain, just easier to draw. Fully protonated, plus for the amino, 0 for the carboxyl, side chain is 0. Overall, +1, 0, -1, -2. So there's my Zwitterion again. Again, +1. So pK1. Again, this seems pretty straightforward. So if I told you for any amino acid, you always average pK1 and 2 to get the isoelectric point, I'm going to tell you every amino acid always average pK1 and pK2. Would I be telling you the truth? Would you say truth is his, or would you tell me lies are his? Would you call me a liar or a truth teller if I said you always average 1 and 2? I'm lying to you because what do you know? You know I'm male, so what's true if I'm a male? Lies are his. His lies are basic. So consequently, this is where the separation kicks in. For lies are his, you have an amino terminal, but you also have a side chain. So they start out +2. So how many times do I need to deprotonate it to make it neutral if it starts out +2? 2 times. Perfect. So, whoa, is it really this easy? If I know this number, do I know this number? Yes, it is really this easy. Isoelectric point, don't make more out of it, just recognize this. For single amino acids, it is always an average of pK1 and pK2, except for which ones? What is the exception? What do you mean by changing the nomenclature? Oh, yeah, so good point. Okay, so the nomenclature is for amino acids and for anything in general. PK1, 1 represents the first proton to come off. Therefore, is PK1 always the most acidic, the first one to come off, and therefore the lowest number? Sure. We go from PK1, that's going to be the carboxyl terminal. PK2 depends on the amino acid. I want to be really careful in this because for something like this compound, this is actually a little more acidic because it's close to this. So your second one's going to be the amino, and the last one's going to be this. But for histidine, the side chain would be second in the N terminal. So PK1 is always the first one to come off. PK2 is the second one, PK3 the third one. So lowest number, PK1, second lowest number, PK2, and so forth. And it's not that you are confused or anything, it's that it is confusing. It is inconsistent from one to another to another to another. It totally depends on the compound itself. So yeah, carboxyl terminal is always 1 because it happens to be always the lowest, but after that, it's a crapshoot. You have to look at it. So, and that's the thing. Some things you can make easy, like this number being this number, that's easy, totally true. But assigning the pKs That's the tricky part. We'll get into that in a second. Okay, so in summary, diprotic amino acids, 1 and 2. Acidic amino acid, 1 and 2. Basics, 2 and 3, meaning for everything except Lysar his, 1 and 2. For Lysar his, 2 and 3. For single amino acids, then, is PI pretty easy? Not so bad. So let me throw a question at you and see how you do. You have 10 seconds. Choice A, good or bad? A is bad because you never average PKs that are far apart. It's always consecutive, 1 and 2, 2 and 3, 3 and 4, always sequential. So 1 and 2 for aspartic acid, that's out. Lysar his is part of the Lysar his collection, or lysine is part of the Lysar his collection. Looking good. Alanine, alanine is one of the 1 and 2. Histidine, 1, 2, and 3. So best answer, B is in beautiful. I totally got it. Okay, so for a single amino acid, I'm going to tell you, isoelectric point is easy, not a challenge. That said, how many had a professor that made you look at a protein as opposed to an amino acid? How many had a tripeptide, polypeptide of some sort? So anybody have a professor that focused on that? One, two, three, pretty much everybody. So now it's going to take a little more work. So I'm going to tell you the shortcut in advance, and we're going to work backwards to it. The rule is still going to be this. Whatever the charge is when it's fully protonated, that will always be this number, which is always this number. They will always go together. So as long as I know that it's +3, do I now know that it's 3, 3? I mean, it's all going to match. So whether I do it this way or this way, as long as I know this charge, I know that. What are the things that are going to make a plus charge? So we already know the N terminal carries a positive. What else can carry a positive? R groups of Lys, R, and his. That's it. So I don't care what protein you give me and tell me all the wonderful things about it. All I care about is that of an N terminal, how many lysines, how many arginines, how many histidines. So this might have been a protein with an N terminal and 2 lysines, an N terminal with an arginine and histidine, N terminal with a lysine and histidine. I don't care what it is. I just know I have 1 N terminal and 2 of this group for a +1, +2, +3. So average PKs 3 and 4. +3 means PK3 makes it neutral, PK4 takes it from neutral, so average those two. Okay, so let's see if I can apply this. How many are on board with the trick so far? So far, so okay, that all I care about are Lysar his. Important. Okay, I'm gonna sort of apply this specifically to the shortcut handout. And shortcut handout basically means that in the handout, there's a shortcut. There's 2 questions in there. I want to pick up on one that we did yesterday, and then I'll come back to isoelectric point. But again, how many definitely had a question, what is the charge on a given protein at a certain pH? No, this is not at pH 7.4. I'm actually assuming pH of 1. So let me ask you just a question. If I have a titration curve, no matter what pH I start out with, is a certain equivalence point always going to be in the same spot? So if I have a curve that goes up and up and up like this, is that point always going to be in the same spot whether I start here, whether I start here, no matter where I start, it's always going to be in the same spot? Curves have a certain issue to them. So because I can get confused, I can start so many different spots, I'm going to arbitrarily say, from now on, I'm always starting here and going to here. So what if they tell me pH up here? I'm going to say, I don't care about that pH. I'm going to cheat and go here. Or if they tell me starting this pH, I'm going to say, I don't care about that pH. I'm going to start here. So in other words, I'm always going to set up a question to make my life easier. So I'm going to assume a pH of 1, and what do I have to do to get to isoelectric point? So if you do it that way, have a systematic way to do it every time, and don't get blurred by some of the numbers they put up there. Just stick to your pathway. No matter how much they put enticing things over here, that's what I'm going to do every time. And it ends up, it's systematic and it's easier to get there. Okay, for this one, the chart I had yesterday, and again, I want to reiterate what's on the chart. Does the chart include the basics? Lies are his. And does it also include the two compounds that end in the word acid? These are the only things that carry charges. The C terminal, CDE, H, N, K kind of messes up my alphabetical order thing, and R. Side chain, roughly 2 to 3. Side chain, I'm sorry. C terminal, roughly 2 to 3. N terminal, roughly 9 to 10. Side chains of carboxylic acid, close to 4, not precise. Histidine around 6. Lysine around 11. Arginine around 12. Different books are going to give you different numbers. I've seen some books list this as high as 13, some as low as 11.8. So whatever. I mean, they're going to give you a variable. So one book might tell you 11.5, one 11, or 10.5, 10.8, 11. I'm fine. Key thing, take this number, and it's 6.8, that goes right there. So at 6.8, would you agree, anything where the pH is greater than pK, so 6.8 is greater than these numbers, that means they're going to be deprotonated. 6.8 is less than these numbers, so it's going to be protonated. So only thing I care about, again, are 6.8, D and E carry a negative, K and R carry a positive, the N terminal and C terminal are going to cancel, and the key thing, histidine, is going to be a 0. So going through this one at a time, A I don't care about, C I don't care about, K I care about, K is a plus, E I care about, E is a negative, Y don't care, F don't care, H 0, I don't care, L don't care, D negative, K positive, E negative, G I don't care about, G I don't care about. So N terminal, C terminal, they cancel. I only care about Ks, E's, the D's, and the R's. So overall, -1. How many are okay with this chart? How many are fine that you can work your way through this? Like, did anybody actually write it down and practice it all? And as somebody point out, if you do this enough, it's just in your head. I think, Sophie, you're the one who said you've done enough of these that it's just sort of been beaten into you mentally. Yep. So it's just so if you do this 3, 4, 5 times, you stop having to do all this. You already just sort of get programmed to know D and E, K and R, and sometimes H. Comes with exposure. Okay, screenshot if you want to. I'm going to get rid of this page. 3, 2, 1, and isoelectric point shortcut. Again, we're going to start at a very low pH. So I'm going to say assume a pH 1. Let's always start at titration curves at low pH and climb. I'm just familiar with that. Then we figure out the charge. So it ends up the only things that carry charges, plus charges, N terminal, lies are his, just like we said before. So I only care about N terminal, K, R, and H. So kill the MCAT. We've got to figure out what I have. Okay. So somebody just put something in the chat box. I want to elaborate on this. Incorrectly mentioned weeks ago that you cannot brain dump on the MCAT, but the correct statement is you cannot brain dump on the scratch paper before you begin the section after a break. This was meant relevant to writing down this pH shortcut. Yeah, because I'm a firm believer you should write this down. It depends on the center, whether they enforce it or not, whether it's even a rule or not, is all in their interpretation. I'd write things down. I think this is really good. I didn't follow up on that. Somebody else did, which is really, really cool. So it's actually, you need to thank a classmate that did this. And by the way, one thing I forgot to mention yesterday, speaking of thankful things, registration is next Wednesday and Wednesday and Thursday, I believe, if I've written down my dates the correct way. Is that correct? Thank you, classmates. So awesome. We're going to be on Discord. I'm going to get on around 11:30 East Coast time, 8:30 West Coast time. And we're just going to go through the registration together and hopefully work as a team and make it all work out. But that's why I've been trying to push you guys to jump into Discord a little bit early. Yep. So next Wednesday and Thursday. So as a team, we will register and you will be very pleasantly surprised that you are going to get your centers. And again, I'll go through, I'll send pictures and screenshots to you probably on Monday, Tuesday, right before, to expect what the pictures will look like, and we'll be set. Okay, so for this one, K, N terminal, K gets a plus, I, L, T, H, I don't care about, E, care about, M, C, A, T. So, oh, I'm sorry, E doesn't matter, H matters, so I have these, I have no R, but I have one N terminal, one K, 0 R's, one H. So 1, 2, nothing, 3. So plus 3. So what do I do? Yes, center locations, look up, and the problem is if you go online right now, look at center locations, they don't have a complete list. So I stopped putting one out because what happens is on the day of registration, it will automatically default based on your zip code to the nearest location to your zip code, and you have to manually change to a different one. Also, pre-register. Every one of you needs to go to AAMC and get your information in so the registration day will go faster. Just a heads up. Yeah, and so they'll give you the nearest location to your zip code, but on the day of the MCAT, there'll be new centers added in. And it's just because what happens is the one they have is a generic list. Those are the centers that are always available. There's some that become available some days and aren't available others. And so you might get a real pleasant surprise that your center could be literally within walking distance on one day and then miles away on another. Okay, so average PKs 3 and 4. Now I need to figure out which are which. PK1 is always the lowest number, so PK1 is always your carboxyl terminal. PK2, I got to do my checklist. Do I have a D in this compound anywhere? No D, so I don't care. Do I have an E anywhere in this compound? Gosh, sounds like Wheel of Fortune every time I do this. I like to buy a vowel, give me an E. I got 1. So that's my next numerical one. That becomes my PK2. Do I have an H in the compound? Yep, 1H. So that's my PK3. I always have an N terminal. That happens to be PK4 this time, because sequentially it's my next one up. Do I have a K or an R? No R, but I got a K. So that's going to be my PK5. So now I've identified, how many agree that was actually harder than deciding this number? How many agree this number is easy to get? Assigning the PKs, was that the hardest part? Knowing where I need to practice helps. So PK3, 1, 2, 3, the H, 4 N terminal. So I need to average the H in the N terminal, 6 and 9 to 10. So it's around 6.1. I'm going to put it right in the middle, 9.5. Yes, so the assigning of PKs goes as follows. PK1 defines the one standing for the first proton to come off, most acidic. So that's my lowest number. Lower the PK, stronger the acid. This would be next lowest if it had one. So does it have a C terminal? Yep. So I've got PK1. So now I decide which one's PK2. So I go next on my list. Is there a D in it? No D. So I go next on my list. E. Is there an E? There is an E right here. So that's my PK2. So this was PK1, didn't have one. This is PK2. Histidine is PK3. PK4, PK5, and I didn't have one. So it always ends up being just a sequential list of what you have. So does that make sense where it comes from? I would definitely put this on my ongoing list and use it so much that it's programmed in. Oh, you're welcome, because this is always the hardest thing for people, assigning the PKs. And once you have it down systematically, it'll be easier. Because how many agree the math is easy and counting up your N, K, R, and H is easy, but this is the hard part. As long as I know where I need to do the extra work, I'm good. So 15.6, average out 7.8, perfect. 7.8, this one's gonna be neutral. Okay, gonna try this one more time. So screenshot if you want to, because I'm gonna get rid of this. So it's clicking in 3, 2, 1. So for this compound, again, we're going to assume a pH of 1. So the things that are protonated, do an inventory for me. How many N's, R's, K's, and H's do I have? How many N terminals? 1. Any arginines? Yes, PKs will generally be given. Okay, let me rephrase this. Generic PKs, you need to know roughly what they are. Specific PKs will be provided if they want a specific number. But you have to know 2 to 3 for a carboxyl terminal. You have to know 9 to 10 for amino terminal. And even then, it's a little, I mean, you're going to find carboxyl slightly below 2 every now and then, or an N slightly below 9. But need to know those. You have no R's. You have 1 K. And you have 1 H. So what's the charge when this is fully protonated? Yeah, it's just the way it works. So what's the charge when fully protonated? +3, exactly. So what do I average? What PKs? Perfect. PKs 3 and 4, exactly. So assume it's fully protonated. That's what we did. Count up your N's, your R, K's, and H's, and you end up with this number right here. So now I average that. So it's +3 means PK 3 and 4. Easy enough. Now to assign it. What is always PK1? What is always the first proton on any protein? That's the only one I know and can lock in. Carboxyl is always lowest. Perfect. So PK1, carboxyl. Do I have, what's next alphabetically? Let's see. I went from C, D, E, H, N, K. They messed me up there. So check. Do I have any D's? Perfect. So that's my PK2. Do you have any E's? I do. Do I have an H? I do. Do I have an N terminal? I do. Do I have a K? I do. And do I have an R? Nope. So my PK3 was glutamic acid, 4-ish. My PK4, histidine. So how do we read 4 and 6 or 10? 10 cut in half is 5, so it's 5-ish. So if you told me 5-1, 5-2, 5-3, is that close enough for a good answer? Yes. So my question to you, how many feel that if you do 3, 4, 5 of these, you will have it mastered and be able to get isoelectric point instantly? It will be your easiest question of things that are supposedly hard. It's an easy way to do it. And again, I always assume pH of 1. And the reason being, I like easy. There's no rhyme or reason. It doesn't have to be done this way. I choose it only because easy is good. So repeat, easy is good. No, that's not a dumb question. That's an MCAT thinking question. Is there a way to get rid of instead of saying only, can I say, is there a way to have 0 N terminals and 0 C terminals? You've just come up with a great trick question that shows up in the bio book because the bio author was kind of mean that way. Cyclic. Are there ever cyclic proteins? Rare, but yeah. So basically, you just come up with an exception to the rule. Yeah, then I just wouldn't have a C and wouldn't have an N. I do the exact same thing. So anyway, I think he purposely wrote ways to screw with us. So they give you the structure. Oh yeah, definitely. Okay. Oh, it's time. Sorry. Talk to you in a minute and a half. Okay, for this one, what do I average for hydrophobic? So B, average PKs 1 and 2, just plug numbers in. So the question was, if we don't give you pH, for isoelectric point, they probably won't give you a pH. Always assume pH 1. Just make that your first step. No matter what they tell you, what they give you, if you want isoelectric point, start at pH 1, always go up a titration curve. Just it's easier to pick one way and do it the same way every time instead of trying to have different ways. You're still going to get to the same point. So in this case, hydrophobic means average 1 and 2. 1 and 2 would mean somewhere between 2 and 3, and somewhere between 9 and 10. So how many did 2 to 3, about 2.5, 9 to 10, around 9.5, 2.5 plus 9.5 over 2. Over 2 equals 6. So 6 plus or minus. Or low end 2 plus 9 over 2 is 11 and a half. 3 plus that is that. Does this bother anybody? So let me just get rid of all my scribbling and just leave that. Can anybody explain why so many people would have picked C? And I need to say, a few years back, remember when clickers were all the rage? In fact, how many of you had to buy a clicker and your professor never even used it? Or maybe they overused it. They were either totally into it or not at all. Well, I went clicker crazy for about a year, maybe a year and a half, and just data point collection. And I was so into it. And I finally said, this is so silly. But at any rate, it helped me at least. It got data from a couple groups and it really helped me. And it helped me why people picked C, exactly. They thought hydrophobic is neutral, neutral is 7. Really want to emphasize this. Neutral for isoelectric point is 6. So hydrophobic's around 6, meaning if you do isoelectric focusing, at the end of isoelectric focusing, where will most of your proteins be found? At what pH? Around 7 or around 6? Around 6. Okay? If you have a column and a bunch of proteins bound, if you change the pH to 6, you will release most of them. Just one of those information or interesting facts. For this one, help me what mattered. So Stephanie, your question was so awesome before, because that now told me there's an N terminal, C terminal. Okay. Did 37 matter? Didn't matter. But only positive charges. Lysines mattered, arginine mattered, histidine mattered. I don't care, I don't care. So I did my inventory, and I had one of them. H1, K2, R1, plus 5. How many blew it through it that easily? How many did exactly that? Just systematically counted things up? Perfect. Nailed it. Fairly easy. Oh, so the previous one, for whatever reason, we think hydrophobic is neutral, and neutral is 7. It's just sort of our programming coming out of GChem, and you need to break that pattern. Hydrophobics have PIs around 6, not 7. And then why do aspartic acid and glutamic acid not matter? Because when they're fully protonated, because again, I'm assuming pH 1 because I like easy. At pH of 1, the charges are plus, 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 0, and 0. I don't count them. So if you want to add them in there as zeros, that's fine. But because they're fully protonated at pH 1, where I'm assuming, because I want to start out at the easy pH, I just ignore them. I only care about Lysar, his, and the N terminal. And it's one of those things, it will come with exposure. And like everything, and like we're all good at some things and they come quick. We're all bad at other things. It takes a lot of work. This is going to be one of those things. Some of you will get it after 1 or 2 examples. Some may have already gotten it. Some 4 or 5. But everybody will get it with a little bit of exposure. Sounds like a virus. So plus 5, average PKs 5 and 6. Last topic of the day, which I'm just going to basically have out there in writing, but the primary sequence, the peptide linkages, the secondary, the backbone, tertiary between side chains, and then quaternary, it's between 2 different subunits. How many have learned this at different points and just sort of know it more or less? They say like nearby interactions. So I'm going to put a reagent in here, and it's going to mess with you. But what does urea do? Breaks H bonds. Which means, in theory, could it mess up quaternary? Sure. Could it mess tertiary? Mess up secondary. So is it a denaturing agent? Does it break this down? Perfect. Okay. Beta mercaptoethanol. I'm still hooked on that one, so forgive me, because there's also DDT, but DTT. Oh, now I'm brain farting this, but for this one, breaks cis bonds. So can that mess up those? Perfect. And then last but not least, why would I use an aprotic solvent? What does aprotic solvent do? Going all the way back to the very first thing we asked, which is a structure you normally see. Aprotic. Oh, what did I spell next to that? Oh, clearly, come on, you can clearly see this is beta. So, yeah, so I'm so sorry. Thank you for somebody typing it in. My scribbling, especially when I start getting down this corner, mercaptoethanol. And so, Jonathan, thank you so much for tossing in the chat box. Really appreciate that, because yeah, when I have writing issues like this, and it's hard to make fun of myself in the middle of this, but yeah, it's beta mercury. You should see that, dang it. BME, beta mercaptoethanol, shorthand for it. Aprotic solvent, no charges. If you have no charges, you have no electrostatic interactions holding things together. And anything hydrophobic interactions will now want to go into the solvent. So if we do this combination of urea, beta mercaptoethanol, and use an aprotic solvent, we can untie the protein into just a long chain with a bunch of ureas hanging off it. So now I can sequence it. So I do all that so that I isolate the primary sequence. SDS page, something totally different. SDS page, oh yeah, well, you're right. We do use this SDS. The only thing is, whether we use these or not is open to debate. So I don't want to say these are automatically tossed in there, because sometimes I do and sometimes I don't want to denature it to travel differently. So I'm gonna say, yeah, maybe not. Keep an eye out for that, whether they say it's reduced form or native form. Yeah, no, you're absolutely right. The question is, this means no charge, so no H bonding? Exactly. It won't H bond with it, which makes urea bind this even more tightly and makes it not fold back on itself. And it's still going to be polar. It's going to be a polar compound, but it's not going to interfere with the H bonding. So urea is going to be the only thing H bonding the structure. It won't bond with itself, and it won't H bond with the solvent. It'll H bond with urea. And so you keep it from renaturing. You get rid of charge interactions. You get rid of hydrophilic or hydrophobic because it'll go in solution. Get rid of H bonds, get rid of cross-linking. To sequence, you basically want to get rid of everything. You want to denature the protein. You want to untie that shoelace into an easy to cut form. Okay. Last question of the handout. Electrostatics cannot exist anymore in an aprotic solvent because charges don't exist in an aprotic solvent. So just like in the very beginning, we put it in a lipid, the charges went away. Okay, so for this one, got a C vote. I'm liking it. Lots of C votes. And then the question, lone cysteine. Did they mess with me? Disulfide linking is almost always tertiary. How many learn that? Tertiary is typically what holds it together. But in general, amino acid chains, protein chains, polypeptides will have 2 or 4 or 6 or 8, but an even number of cysteines. So it can have intramolecular disulfide linkages. Very rare. Very rarely do we ever have an odd number. But if we only have one cysteine, can it bind to itself, or does it have to bind to another strand? Has to be to another strand. How many feel this is a trick question? How many feel that I picked on something that you normally think of as one thing and gave you a special case? I did, but I was inspired by something they had done. 18 amino acids didn't matter. It's just the fact you only have one. So primary and secondary, that isn't it. It's got to be either tertiary most of the time, in this rare exception where it's quaternary. So again, why did so many people pick tertiary? It's almost always found, usually found in tertiary. Perfect. Leading to, so I'm about to click and it'll go to the next slide. Oh my gosh. Is that a jet? Is a jet a verb or a noun? It's a verb. So I do apologize. This, I mean, hopefully gave you enough of a heads up. We're going to go about an hour overboard, ends up being counting break and all that, 45 minutes extra. Just want to make sure, took time to go really slow through a lot of things, and especially things that normally would have been covered beforehand. So that's it. This, if you need to dart out, and hopefully, I'm glad it was helpful. And I can go back to things. So go back to question 6, screenshot it, most definitely. I hope I can still have drawing on it. So let me get everything coming in. Oh, sorry. Shoot. Okay. Give me a second and hopefully it'll pop up. It's because it's playing catch up. I don't know where it is. So I think that should be good. Okay. I think, is that good? Oh, you're welcome. Sorry to tease you like that, make you wait around longer. Oh no, there's absolutely no homework from yesterday. Yesterday was sort of the intro. This is what you're getting yourself into. Homework starts today. Pre-reading started today. So this is officially your first phase 1 that you should be doing sometime this late afternoon or evening. You should pound through that.
Todd, I have a quick question. Will we be looking at buffers in a different lecture?
Yes, exactly. Okay. So yeah, the acid-base lecture, that's why the acid-base lecture was supposed to come first, and titration curve, because yeah, that becomes critical. But yes.
Okay, great. Thank you.
You're welcome. And then to study, well, the question is, when recommend to study Strecker and Gabriel synthesis? I think passages, just learning it in context, because the concept should be simplified to what do I have, what do I need to add for both of them. So just sort of make a flow chart of what I have, this is what I need, and sequentially this is how I add it, and then apply it to questions. It's only good if you can apply it. So memorizing the entire synthesis isn't going to do as much good as, okay, what kind of questions am I seeing? I mean, so the question is, why can't charges exist in hydrophobic solvents? Let's take the typical example they give me, Na plus and Cl minus. Do you agree with water? Water solvates it. Good on this one. Is that something you've seen before, that salt dissolves in water because water can hydrate it? Sure. But what if it's not water? What if it's oil? If it's oil around it, does oil interact or no? Oil's not going to interact, so therefore, this sodium and this chlorine are going to want to come back together. Charges don't like to be in oil, so they're going to stay together. So what happens with the protein then, it has a unique situation. It has an NH3 plus with an R group, has an RCO2 minus over here. What it does is it transfers a proton over here, so that now becomes H2NR. That becomes H. So instead of becoming an ionic bond, just transfers a proton to become neutral. And so they don't have charge interactions because they no longer have charges. They transfer that H away. Yes, so homework, I'm scrolling back up through the questions as they come in. So I know there's a few that I backlogged on, but Jonathan's question, so this is what we're looking for, right? Homework phase 1. Oh yeah, that part. Yeah, for this one, I chunked it up a little bit because some of the passages, some of the homework passages fit with another lecture, lab techniques lecture. And so again, it's that the lecture and the book the book is always a little behind the lectures on that one. But yeah, that part, exactly. And then, oh, you're welcome. Probably already gone by now because it's gray. General question, are we still allowed to attend lectures from other sections? Oh, Mo, I wish there was another section. In a perfect world with 50-something people enrolled, what we would have done up until this last summer was have 2 and possibly most likely 3 sessions. Josh is in charge completely of scheduling this time. I stepped away from it and letting him make all those decisions. He chose 1 session. There is no other lecture. I did other lectures last week for this one simply because that's just me. I'm going to do that for mine. But unfortunately, there is no quote unquote second lecture to attend. They're gone. So it's one and done. Somebody mentioned yesterday, can we film? Just want to make it clear, legally, we can't let you film because nobody signed off on not being filmed. However, there are programs out there I know people have called Snagit and a few others. And there have been cases that I believe people may have filmed. And boy, what can we do? We can't identify who filmed it. So it might be something to ask around if anybody is catching it. That might be the best bet. And so if we had multiple lectures, I would be upset, but we don't. We should. And as such, if it ends up getting recorded beyond our control, it just does. Yeah. Oh, and Stephanie already answered it. Yep. This fall, for the first time, literally in our history, we don't have multiple sessions. So still not sure Josh's logic, but that's the way it is. Yeah. So yeah, it was doubled up. Yeah. Oh yeah, catalytic triad. Yeah, I'll go back to that real quick. Yeah, I got the email yesterday. I'm so sorry. I got buried on doing something else, and I sincerely apologize for not getting back on that one. But yeah, that one would be perfect to talk about. Oh yeah, exactly what you just said. I'll respond to that one based when I log off of this. If you're still here, you are still here. So yeah, I will. Yes to what you just said. Oh, writing or not writing in the book? I don't know what the answer is. I'm a firm believer writing equals remembering things. So I'd write all over the things if it were me. But also, it's nice to keep books pristine and write on a note somewhere else. I mean, just because then you can go back to your books and not biased. And hell, they have better resale value. And just word to the wise, as the books are getting printed in the future, your books' values will go up because I'm guessing that the philosophy is going to be take more out and try to sell it in a different package. Another story for another day, but up to you. So write it to learn, leave it pristine if you want. Okay. Oh, unfortunately, somebody already asked about digital things and they've already taken off. Shoot. Okay, so let me go back to the question that's catalytic triad. I'll make a blank page. Oh, first question, catalytic triad. Yeah, so it's kind of weird. Bases aren't defined by their pK or pKb value. They're defined by what they do naturally. So histidine, if you put it into water, it will be more likely to pick up a proton, i.e. act like a base, donate, get a proton, than it is to give off a proton. So it is more basic than it is acidic, if that makes sense. So we call it basic because the base it reacts more in a basic fashion. So keep in mind, that's a pK of the conjugate acid that the pK6 is for. So histidine, when it's neutral by itself, that compound, they consider basic. Well, yeah, one of the weird catches in biochem, the acidic molecules typically exist as bases. The basic molecules typically exist protonated as acids. So most things exist in their conjugated form. But let me just write this down so I remember it. One, cat triad. So these are the things I need to go back to. as I'm reading through, I want to make sure I don't skip anybody's. Okay, so the multiple lectures, yeah, somebody else. I sincerely apologize. It was my typo in that, because quite honestly, I write the letter to everybody early on, and I wrote it based on the schedule I submitted, and then in the middle of August, just decided, you know what, you run everything. You take over. You hire the teachers. You run the schedule. And I stepped aside, and I didn't pay attention that it was one lecture instead of two. There are no multiple lectures. So if there was different sessions, it'd be great. There aren't this time. So, and I, again, cannot tell you. Oh, yeah, so homework. Okay, for homework, that is true. So maybe I'm way behind this. But yeah, for write in pencil, then go over it in blue ink, and then finally red ink. And it just color codes what you know. Okay. Yeah, thanks for that. So yeah, for the repeat person, reach out to me, and I will, let's talk if there's a way to deal with that. Okay, let me go back. There is no longer a session 1 and session 2. Yep, and again, not sure why. Yeah, okay, so the question is, are we gonna add anything extra? Did most of you get an email I sent out yesterday about Patricio being around? I'm gonna be around. Patricio is the other really veteran teacher. He's been around for like 20 years or so. Between the two of us, we will mop up certain things. And mop up means stuff that was removed from the schedule when it turned into this new version, which included equilibrium, periodic motion, and stoichiometry. I want to wait till after some of those lectures that could include them have been given to make sure that stuff isn't given. And then, yeah, I'll end up doing some mop-ups. And mop-ups will end up, I mean, I'll have to figure out what day, but I think Sunday evenings was the plan we'd talked about. Yeah, I'll go back to Strecker. And ask all money questions. Ask of Josh, because that used to be something we did. We actually, wasn't referral. You signed up in pairs and you each got a certain amount off, because we originally wanted people to always study with friends. But yeah, Josh does all money things now. He's the money guy. So I'm passing the buck, and you can probably tell from my tone that we're moving in a direction that just, it is what it is. So sorry for that. I mean, my job as I see it, I want to do as much as I can to help by offering as many lectures and office hours. But I'm stepping out of the company that I started 29 years ago, and it just really comes down to just ideological differences. And that's why I'm passing all money questions there. I've stepped away from that aspect completely. So apologize, I'm totally passing the buck, literally. But it's just, when my business partner passed away and things changed, it just, I don't think changed for the best. Okay, totally unprofessional. Let me just go back to question 1 and leave all that alone from this point then. So question 1, catalytic triad, and there was something else, and hopefully you'll bring it up. But first off, so question number 1, oh, what now? Are there 2 sessions now? Is that what it says on the website? No, the only one I know is 2 to 4. Just Josh put everybody into 1 session instead of 2. So he canceled both sessions and made a combined hybrid session. That's the last I saw, but I haven't been on the website since then. So if you see something new, I mean, I'll go look and see if that's true. But this time I believe it's set. Yeah, I mean, nope, not sure. But anyway, let me go back to this question. I'm going to erase everything to start from scratch. So in this one, we know that we're looking for amino acids. So amino acids have a carboxyl terminal, an amino terminal, a carbon with an H, and an R group. They have a carbonyl, nitrogen, carbon with an H, and an R group. So basically in this one, we're trying to identify the amino acids that are put together. So we're basically, do you agree the only difference is the side chain? That side chain is valine. This side chain so it has an H and an H and an H. Okay. Does that make sense? So for everyone to see this one again, does it make sense that you're breaking it down into looking at what the R group is here, the R group is there? So valine and cysteine. Perfect. Okay, and would you agree this is a tough question? This is a pretty challenging question because it's in a weird sort of format. Okay, and then catalytic triad, if it's okay, I'm going to go back a couple more steps. Shoot, okay. Sorry, it just takes a second for this thing to play catch up to get to the right screen. So catalytic triad, I'm going to just click to a certain point where let me get rid of. Okay, let me just mention what's meant by catalytic triad in this specific example. Okay, so catalytic triad has the following. There's something happening at the center of the enzyme here, usually a metal and a substrate that get bound. Okay, so if this is going to attack, how do I make something a better leading group? So is there a way to make something a better leading group from what you learned? Protonate it, exactly. So step one, protonate substrate. Step two, attack that protonated substrate. And then number 3, neutralize product. Make it what you want and reestablish the enzyme. So a lot of times just these pathways, these active site processes are predictable. Protonate to make a leaving group, nucleophile comes in and attacks it, kicks it out, and then deprotonate back to neutral. Meaning, is a lot of enzyme activity going to involve something like a serine, something like glutamic acid or aspartic acid, possibly glutamic, and something like a base like histidine. Histidine is pretty much always your choice. Serine is often your choice, but occasionally it could be cysteine or selenocysteine. And aspartic acid is almost always your choice, although occasionally glutamic acid might be the one that comes into play. But generally, many pathways have the same sort of active site processing. Protonate it, attack it, neutralize it. Protonate, attack it, neutralize it. And so they just say there's the 3 amino acids that are responsible for it: the nucleophilic one, the protonating one, and the deprotonating one. So is this more memorization than anything else? So how many agree this is memorization? And I totally forget who asked this question. I hope they're still here. I didn't pay attention to who tossed it out there, but yeah, this hopefully makes some semblance of sense then. So this is the basic gist of what we're doing on this one. And so the catalytic triad, it's different for every mechanism, but almost always it's these 3 or 2 of these 3, the different ones. So chymotrypsin is one of the famous ones they studied, but I think something of phosphate protease or something is also one of the ones they studied. And so they're, over the years, they've added more and more. The 3 key enzymes in the active site represent your so-called catalytic triad, the 3 that are doing these respective steps. Visual is really, really key. Totally agree with that. So does it help that there you can see an acidic proton here? You can see a lone pair for a base here, and you just have to believe that that lone pair can attack in. So visually might seem a little better. And then active site, the reason I'm leaving it as open-ended is because it could be a metal, it could be some carbonyl compound, could be whatever in the middle. That's typically what we're seeing happening. Okay, so if you're good on this, was there something else needing me to go back to? I think this was it. Catalytic triad 6 and 1. I will scroll back up and see what it is. And I think, oh, you're very welcome. Yeah, I think that's it. So thank you for, again, always having some things put in. Strecker synthesis. Yes. Apologies for the memory just not being what it once was.